the coffee chat video, as it says in the agenda. We're going to play that here in just a second. And then just after lunch, before we go into the last set of talks, we'll announce the results of the poll, or the polls across the week, and you should stay tuned for that. And then we have 3 more talks after that. Kat Bormann's talk, Micah Sandusky from M3 Works, and then Jenny Fromm from the Army Corps. And so those will likewise be great talks. So make sure to come back for that. Then we'll have some closing thoughts this afternoon. So this video is one that Friant Water Authority did back, gosh, I think they recorded it almost 2 years ago. And I was still at JPL then, but got to go up and meet with them at Lake Tahoe and talk endlessly about snow hydrology and the program. And so we thought it would be a good one to run this morning with some of that background. So Liz, take it away. And then at about 9:25, we'll have Wes Monier's keynote. So make sure you're here for that. We're going to record that and post it on YouTube worldwide. All right. Let it go. My name is Tom Painter, and I'm a research scientist at the NASA Jet Propulsion Laboratory. JPL was the very first NASA center in response to Sputnik and JPL providing the Explorer 1 launch back in 1958, and through the years, JPL helped to develop the soft landing on the moon that led to Apollo 11. And exploration of the solar system. And with the exploration in the solar system, then we started looking for water in the solar system, because where we find water on Earth, we find life. And so the technologies that have been developed at JPL for exploring the solar system, and in particular looking for water, we're turning around and looking at the Earth in this particular case. And so that's how I was brought into to JPL, and in particular to look at water resources and water cycle science.
That's what I was wondering about, because NASA obviously does many things, but it's associated in the public's mind with space exploration.
Right.
So I was curious how it came about that you began looking at better measurement of water resources here.
Yeah, well, it's important for people to know that the very first NASA mission, so the Explorer 1, discovered the Van Allen belts. So it was Earth science from the very beginning, and in the NASA mission statement, Earth focuses quite prominently there. And learning about the Earth and learning about processes on Earth is key then to helping us to understand what we're looking at out in the solar system. The program at JPL started out really in the 2000s, starting to look at water resources more intensively, and then I was brought in 2010 with the intention of building a snowpack related, water resources related program. And so very soon after I got there, I went to my old friend Frank Gerke, who's the chief of the California Cooperative Snow Survey Program for the Department of Water Resources, and talked to him about this idea that I had about how we could measure the snowpack wall to wall and finally get past many of the uncertainties that have plagued them in their snowmelt runoff forecasts. And fortunately, we had this long relationship before that, and so there was a lot of trust in the very beginning, and we were able to partner on this from the very beginning. And so we pursued the program from a water cycle science standpoint to fill that void in our understanding of the snowpack, how it's changing with respect to climate change, what it's going to do for these kids' water resources in the future, and then likewise in working with Frank from the very beginning, we were considering the water resources, water management needs from the very beginning. So from before we even had any hardware or much software at all, we were starting to work on the operational program with them as well.
So once you actually launched the aerial surveys, I mean, did you start that in 2011? What year did that begin?
We started working on it in 2011. We did our first snow-free flights as baseline in 2012. Our first flights in California were at the same time that the Curiosity rover landed on Mars. So we didn't make the media splash that we would have hoped to. But then in the spring of 2013, in fact, April 3rd, 2013 was our first flight of snowpack.
Okay. How does it work with the LiDAR and with the fixed wing, and compare that to the accuracy of the old-fashioned way?
Right. So the old-fashioned way, really, it started in the early 20th century. Dr. James Church, he was a professor at the University of Nevada, Reno. He was a humanities professor, but he had this great interest in answering the question of the Lake Tahoe lake level and really what was controlling that. And so he worked on building the snow tube, which is often called the federal sampler, or by those of us in the community, the Mount Rose sampler, because that's where he deployed it, up on Mount Rose, right at the end of the lake over there. And that really is the home of snow hydrology for the world over there. And then that expanded into programs in California, where the surveyors will ski along, plunge the snow tube in, pull it out, weigh it. It's quite accurate most of the time, but it's a very sparse measurement, and they have to ski many miles off to the next site, and then off to another site, and so it's not a full sampling of the snowpack.
And labor intensive.
It's very labor intensive, but it also is really important even for us going forward. Right? So the way I like to think about it is that it's like the snowpack across the mountains is like your TV screen. And what those snow courses with the snow tubes provide is every once in a while you have a pixel turned on the TV, right? And through the years, through 30 years of those pixels continuing to turn on, you get a fair idea of how much water you're going to get out of the mountains, right? But you do not have the complete picture. And there's quite a bit of uncertainty in those relationships developed from those sparse measurements. So we've known in the snow hydrology community and the hydrology scientific communities for years that we had a very uncertain quantification of the mountain snowpack. And so in the late 2000s, several of us looked at what these new technologies were that were coming along, and LiDAR in particular, which is like a laser radar. It measures how far away an object is, was able to provide us the kind of measurement that we needed to have wall-to-wall measurements. And that technology had really come along in a way that we could fly high, cover the mountains, not run into the mountains, but be way above them, and yet make the measurements all across the snowpack to measure that snow topography We do it when there's no snow on the ground, and the difference between the two is the snow depth. Now, that's not all of the picture. The whole picture is snow water equivalent, which the snow tube gives us.
The content.
Right. So, but fortunately, the variability across the landscape of snow water equivalent comes primarily from the variability in snow depth. The snow density, which is the other part of the picture that you need to know how much that depth turns into water, it doesn't vary much across the landscape, and how it does is predictable. And so we knew that that if we measured the snow depth, then we could really get an accurate picture of that spatial distribution of snow water equivalent. The other piece of the measurement is what's called the imaging spectrometer, and that measures the reflected sunlight in about 100 different colors, some in the visible wavelengths and some out in the wavelengths that we can't see in the near infrared. And that's where the bulk of the interaction of the sun with the snowpack goes on and controls how much energy is absorbed by the snowpack and how fast it's going to melt. You hear a lot about temperature influences on snowmelt, but really the influence of temperature comes in changing snow to rain falling out of the sky. That's where its big influence is. Absorbed sunlight represents about 90 to 95% of the energy that goes to melting snow. And so knowing how dark or bright that snow surface is tells you dramatically, with the kind of accuracy that you want, how fast it's going to melt. And so combining those two measurements then allows us to map the snow water equivalent and its reflectivity, and those two are the big dogs in understanding the timing and magnitude of snowmelt runoff. It's enormously accurate, yeah. It's so the uncertainty is about 8 centimeters for the vertical measurement of snow depth across an area about this size, right? But there's no bias in it. So when we average that up to 50 meters, which is where we make the estimate of snow water equivalent, those errors that we have, those 8 centimeter errors, damp out so that across a 50 meter area, our uncertainty is less than a centimeter in that snow depth. And then the snow density, that's a combination of modeling and the measurements that we have either from the snow courses or the snow pillows, which came into use in the 1980s when people finally figured out what to do with a waterbed. And you put it in the ground and measure snow. So the combination of those measurements that we have out on the landscape with the modeling gives us a very accurate measurement of the snow water equivalent. And so what we have found now with the modeling of how much water is coming out of the mountain basins in the spring is about, the uncertainty is a little less than 2%. And from the historical measurements, the snow pillows and the snow tubes, the forecasts from those, when it's an average year, their forecasts can be quite accurate. They can be in that 2% uncertainty range. When there are excursions, either dry year or wet year, and warmer year or colder year, that throws off those old models. And so we end up with forecast errors. In about half of the years, those forecast errors of how much water is going to come from April 1 out through the end of runoff, those errors are greater than 20%. And in 1 in 5 years, those forecast errors are 40% or greater. And averaging across 10, 20 years, well, they do pretty well. But people's lives are impacted by those individual years that are being averaged out. And with a changing climate, with more rain falling, and likewise more requirements on the runoff coming out of the mountains, greater dependency, as well as a greater federal requirement on environmental flows. What we used to be able to get by with in those forecast errors, we can no longer get by with those. We can't afford those costs. We can't afford those uncertainties. And so being able to follow those excursions from year to year and take those errors all down very close to 0% is key. And fortunately, this quantification of the snowpack has been hugely successful in that direction, even far exceeding what our expectations were going to be of how powerful this resource was going to be.
Okay. So for example, Friant Water Authority, why do they care so much about this? What's the benefit for them?
Well, so Friant Water Authority is a collection of farming entities, and the number one water resource for them comes from the snowpack. In the annual precipitation in California, about 80% of what falls onto the state of California comes in the form of snow. So being able to quantify that from year to year is absolutely key in having that reliable estimate early on in each season to know how much water there's going to be, and likewise for their agreements and moving of water, and being able to let their entities know whether there's going to be a shortfall, there's going to be surplus, what to do about groundwater recharge, etc. So it takes them from a highly uncertain world that their lives were saddled with being in that business, to removing that uncertainty and letting them really focus on optimizing what it is that they intend to do.
So in some ways, does it almost take the place of additional surface storage because it allows them to maximize what they've got?
That's right. As they like to say, you can't manage what you don't measure. And it was pretty remarkable that DWR and other entities have been able to forecast as well as they have with just those very sparse measurements. But we feel really fortunate to have been in the place to be able to bring this to the point that we can really optimize that most critical of resources that's allowed this civilization to exist out here.
So DWR obviously benefits too, because it helps them to manage reservoirs and to know how much capacity exists for the runoff that may be coming.
That's right, and to allow them to make those more accurate forecasts, to help with their flood control program, to help with their push to honor new requirements on groundwater, and to help the entities such as Friant and other irrigation districts, municipalities, with optimization of groundwater recharge, and as well as the operational flexibility between them. There are many tangled relationships that hinge on the knowledge of the water resource, and those entities through the decades have simply had to accommodate these large uncertainties, and they've had to hedge because of these large uncertainties. And at least for this part and the downstream effects, we've been able to really reduce that hedging.
What about other benefits? Does CAL FIRE, is there a benefit for CAL FIRE?
Yeah, absolutely. So every time we fly the mountains, we touch the trees with laser pulses, and we fly several times through the spring, and so we can take those laser returns and fuse all of them from various acquisitions into a very high resolution picture of every tree and how much biomass it has. And likewise with the spectrometer on board, it allows us to have an understanding of the health of that tree. So how likely is it to be sucking water, or is it dead? And then from a scientific standpoint, feeding back to the understanding, how much runoff are we getting in places where there's this intense tree mortality? Are we starting to see more runoff because those trees are simply not active anymore? And not just CAL FIRE, but also the U.S. Forest Service from their forest knowledge, and likewise transportation, recreation. We have these very high resolution measurements of snow depth. Well, all the trails, the Pacific Crest Trail, right? That we can now tell people where there's snow, when it has melted out, and then likewise understanding for Caltrans with respect to some of the Trans Sierra roads, so Tioga Pass, Sonora Pass. What's the snow depth across those roads, and where do they need to put in the most intensive work on plowing? So yeah, we've identified many of these applications, but we also know that once we put these data in the hands of the younger generations who are not afraid of terabytes of data, they will really start to explore the even greater utility that we've never thought of. We also have spent quite a bit of time talking with the Sierra Nevada Conservancy, which is part of the state government, discussing the idea. They have a great interest in the quantification of the Sierra forests, and so they're looking at the idea of maybe a decadal scale survey, very high resolution of the forests.
Okay, enough of that guy.
And then the snow surveys, given the fact that we do touch the forest, but not. Great. I had to switch locations because my internet was poor. So I think that video is out there, and and I don't think there are any egregious statements. There's some that need clarification, I think, but any rate, Liz, are we ready to we're ready to go? Wes, are you ready?
I believe so.
All right. So it's a real joy to introduce Wes Monier. Wes was actually part of the first meeting that we had when Bruce McGurk was introducing the concept of ASO to various cooperators. There was Gary Freeman from Pacific Gas and Electric, Andy McMillan from Southern California Edison, one other person, and then Wes was sitting at the far end, and he was, and I was watching his brow wrinkle several times during the whole description of the concept, and thought, okay, this guy's going to be a seriously tough customer, and it turned out that he's been one of our greatest advocates and one of the greatest users. So Wes Monier is the chief hydrologist for Turlock Irrigation District over in the Central Valley, and Turlock is the oldest irrigation district in the state of California. Wes has not been with them the whole time, he hails originally from Texas, but made his way to California, and he has a physics background and a law background and a hydrology background, and so that makes for always fantastic talks and discussions with him. So Wes, take it away.
Thank you, Tom. I assume everybody can see my screen. Okay, so I really appreciate it. This has been a very interesting and fascinating conference. There's been some discussions And what I'd like to try to do today, without butchering it too bad, is to cover some simple concepts. There's been some discussions by some very smart people throughout the conference, and there's been some themes in here about collaboration. Who's going to collaborate? Who's going to use this data? Who's going to pay for it? What's the value of it? And I want to try to answer some of that in the context of operations. And how would I do that? And putting this together, the operations people that I deal with have seen most of this stuff, if not already. The audience here that I'd like to communicate to is the young scientist and the policy people, and attempt to value what it is that's being done here, that it is going to make a difference, that this is very important. And I hope to be able to show, hopefully, just a small part of that. I've got Olivia Kramer and Jason Carkeet on here. This is my team. But the team, there's a success story here, and it just wouldn't be to list everybody that's contributed to this subject. It'd take all day. San Francisco, Hydrocomp, with Dr. Crawford and Tracy. You're going to see some results from this stuff. And what I want to do is impart, the reason I want to kind of impart on this is to the young scientists that are here, you're going to make a difference. DWR, CNFRC, the Corps of Engineers, all of this success story stands on the shoulders of some good people, hardworking, and we wouldn't have got there without that. And so is there going to be some collaboration going on in the future? Well, there already is. It's just probably going to get a smaller world, which is a good thing. Again, to do this subject, I pulled from our operation reports and what years. These are daily 60-page reports. You've got decades of experience here and work. How do you put this in 20 minutes? It's not easy, if probably impossible. So there's a lot of horse trading on subjects. I'm going to go real fast, and it's kind of the tone that I just want to kind of impart. You all know where I'm at and the people that work with me. So if you got any questions, please give us a call. And so today, what is the value of this to the 12?
Hey, Wes.
Yes, sir.
Sorry, it looks like your slides are hung. You're on slide number 11 and not in presentation mode. And now you're on slide 2. Awesome.
Is that still slide 2, 3?
Slide 2.
You can see the history?
No. Now we can.
Well, then I'm going to leave it like this.
All right.
So TID has been around since 1887. We're part of the culture in the area. And the reason I show this is we are a public agency, 5-member board elected, and this is what the people want. They want us going in this direction. The Tuolumne is 1,500 square miles. It's due east of the San Francisco Bay. It's very easy for me to talk about TID and NMID in San Francisco. I'm doing this subject not a lot of justice in leaving San Francisco out. It's just a time and resource issue. They are a very big player here in a multitude of ways. Don Pedro affects $278 million in annual farm income, $854 million in annual crop production, 18,900 jobs. So if this program has a direct effect on these numbers, and California is the 5th largest economy in the world, I'll let you do the math, but there's a lot at stake here. So in order to understand how we operate, let's look at the stage, the environment that we're having to operate in. And again, this is a snapshot. It's to be real quick. I want to continuously revert back to Dr. Anderson on in his terminology when he says, you know, we're at a stepping off point. Yeah, I hear that. I guess to me, it's a question of how big is that step. So let's look at the short term real quick, and then let's look at some long term to maybe answer some questions. And again, I think you've seen some of this stuff, but this is incorporated in how we operate. You've seen the graph of the hydrology of the Tuolumne River watershed. It ranges from 386,000 acre feet to over 4.8 million. And it's not a 45-degree line, but it's close. We have probably had an average year within 30,000 acre feet of the average, but for all intents and purposes, it's a feast or famine issue. I think you all have seen this graph. The standard deviation has moved from 765,000 to 1.1 million. The coefficient of variation has gone from 0.41 to 0.6. On a water supply perspective, this is catastrophic. This is eating directly into the firm yield. The projects in California, I think in general, one can say that they were, for the most part, probably completed by the 70s, definitely by the 80s. They're all based on hydrology, probably up to the 50s. So the hydrology that you're operating today is not the same hydrology at which the facilities were designed and the infrastructure that the facilities were to support. The 4 driest and 5 driest years have taken place in the last 25 years. What does that mean? And so I went to some tree ring data to try to figure out, well, what does that mean? When you have 2 catastrophic events, from my perspective, really back to back. And this is some tree ring data with respect to the actual full natural flow. It's got an R squared of 0.78. I don't know if that's good or bad. I'll let the scientist here determine that. I wouldn't put much stake in that, but I've seen scientific papers done with a lot less. So to me, I guess it's a chocolate vanilla issue. When you look at the difference on an annual basis, that's well, that's not too good. At least I don't think so, but I don't know. When you rank it, sort it, you can definitely see a trend there. And you say, well, maybe I can use this information. Now, on one end of the spectrum, real quick, let's look at the wet site. So in 1862, Sonora had 102 inches of rain through December through January. San Francisco had 34. To put things in perspective, we have 32 inches on average in Sonora for the year, 12 inches at TID. If you scale that up, I come up with 6 million acre feet. I personally think that's low because your efficiency per inch as you go up gets better. I would like somebody to tell me what that flow is for that flood that they had back then. I guess my point is that on the wet side, well, I don't know how valuable this is, but let's go to the dry. And again, that's the recorded history with the tree ring data. When you look at a 2-year running relationship, all of a sudden this stuff tightens up real good. You go to a 4-year running accumulation, and it is very impressive. And I'm not a biologist here, but I can make some assumptions that the tree is doing everything it can do to survive, and so every drop counts. But the point of this is that the 5 of the 6 driest years are in the last 32% of the history. The 2 driest are 91 and ending 2015. Now, up in 91, the comment was, well, that's the dry, you could argue that that's the driest in 1100 years. You may get into a discussion, well, there's reasons that might really not be, it might not be the exact driest because of the inaccuracy of the tree gap. But from my perspective in water supply, you just call it good. The differences are negligible. But the 2015, based on this calculation here, was 19% lower than 91. So if the 91 was comparable to the driest in 1100 years, my question to everybody has been, well, what does that make the 4-year period ending in 2015? If you beat the previous one by 19% on your distribution curve, it's got to be a hell of a lot more than 1100 years. What does that mean? I don't know. This graph here, I started to take it out for time purposes, and I thought, well, no, I'll leave it in there. I don't know what this means. It goes back to the old physics class where life's a harmonic oscillator. I'm just looking at this thinking, well, you impart this data on going forward, I think there's going to be some issues. This graph is from Scripps. Now, up to 1997, it was kind of codified that you do not have warm storms in the winter. After the 97 flood, the Corps of Engineers called us up, and a gentleman by the name of Paul Pugner came in. I remember this was to get ready for 1997 to be the wettest year on record, equivalent to 1983 due to the El Nino effect. And the Corps wanted to know what we were going to do to get ready. And he said, by the way, you can have a warm storm in the winter just as easy as you can have a cold one. And I remember that, and I thought, oh, well, that's an interesting, what does that mean? So then we get to 2017, and for me, this was a record-breaking year in a number of circumstances in that we had the largest rain event, and as you see here on this graph here, the 1997 flood and the 2017, you can see that as it moves up the Y scale, there's actually more distance. And then this graph ends in March 7th, but I've seen this done. I think it was actually presented at this conference. They take that on out, and it is also the wettest year on record. It beats 1983. So we have rain events and snow events, and the largest on record. What does that mean? I'm not sure yet. So now let's get into the forecasting based in this environment. And conveniently, for this purposes, we have 2 years back to back of extremes that can value what we're talking about here. But before we get into the wet 2017, let's drop back to 1997. This is the Don Pedro storage and the Tuolumne River runoff. And so we were coming in December of 96. It was very wet. It was raining, 1,500 foot snowmelt elevation. So every time it rained, the full natural flow had died. We were going through several iterations. I think we went through 3 iterations on this, and you can see that we're encroached. Not a lot, and we'd get encroached, and then as the rain would stop, we'd start bringing it back down. Then it'd rain again, and such. So it was kind of methodical. Snowpacks building, and then on December the 26th, which was a Thursday, I get a phone call that says, you've got 4 inches of rain on Saturday and 4 inches of rain on Sunday. And well, what does that mean? And the comment is, well, when you get it figured out, let us know. And there's a bunch of things that go through your mind, like, now what do I do? And so and some of this talk it was brought up, what's the relationship between the policy people and the scientists that this technology that we're working on develops some trust with the policy people that they can trust the technical on what it is that needs to be done. And there's value in that. And so in that stage, in that particular event, the policy because of what are you going to do about this? Well, we're not going to do anything about it because we're already maxed out. We can't increase the releases because we have flood control requirements below the reservoir. We have a creek, dry creek that comes in at Modesto up above the gauge, and we have to maintain 9,000 CFS. So if it's raining locally and flows are coming in, we've got to keep the releases at Don Pedro down. So there's nothing we can do. And so what happens is it starts raining again, and the reservoir, of course, goes up, as you can see there, and then we hit the spillway, and the water comes over the spillway. And then after it quits raining, it drops back down, and you see the hydrograph there. Now, that was a totally reactive environment. You wake up one day, you've got this piece of information, there's nothing you can really do about it. You hang on and hope for the best. You hope for things like, well, maybe we'll get lucky. The storm will move south or west. And in fact, this second curve here, it did. The forecast for the rain coming in this period here were a lot more than the January 1 event, and they went north. But the point of this discussion right here is that without this information, you're just in a reactive mode. When you contact the Office of Emergency Services to tell them to get ready, you're not going to give them information other than, well, we think there's a good probability we're going to open up the gates. Well, how much? You're going to make a guess. I guessed 120,000 CFS was going to come into Don Pedro. Actually, it was 121. You have to be very careful to know when you're lucky and when you're good. You better make a distinction because otherwise you're going to get caught. Now let's go from this environment to 2017. There's 20 years. There's a lot that's taken place. After 2017, we brought in HydroComp, Dr. Crawford. We had some real-time models. We're working with the CNFRC, DWR, on and on and on. We've started watching the information from scripts. So December of 2016, we've come off a 4-year drought. And I want to put things in perspective. If you would put your elected official hat on, you're working for a local agency that just went through, at a minimum, the driest 4 years in 1,100 years, if not more. And droughts, and I'm not insulting anybody here, but obviously it's a very gut-wrenching affair. It's very emotional. There's a lot at stake. So as a hydrologist, though, you're watching the runoff. We're about 15 feet below the flood control space, and because of the hydrologic environment we're in, when it's dry, you're looking for that first opportunity to release, and when you're releasing, you're looking for that first opportunity to cut back. So we've had, in 2016, October through December, we've had 16 inches. Normally we have 12. And because of all this modeling, we know that the reservoir is actually, if it quit raining, the reservoir is going to move up because the lower elevations are going to melt off. And eventually around March, it's going to fill. So anything above that, we probably need to release. So on Saturday, New Year's Eve, we're watching this. And this graph here, this to me is the holy grail of graphs. There is a lot going on. This is a 3-dimensional, 4-dimensional graph from my perspective. You've got a spatial perspective, you've got an intensities perspective, and it's over time. So we're looking at this graph here. And it's like, okay, we're about ready. So about Saturday at 9, this is, we see the next update. Okay, we're about ready to come back online. And then the next one comes up, and it's, yes, about 2 o'clock Sunday morning. And this is on New Year's Eve, right? And so, okay, yes, we're going up. And so the emails go out. And so when you send, the technical people send the emails out to the policy people and say, okay, this is what we're going to do and why. And why would you do that? Well, I have the National Weather Service. I have Scripps Institute. In the future, we're going to have the ASO data. And all of this is saying, hey, this is what you want to do and why. Because if you don't do this, then you're really kind of negligent. And there's a process here where it takes time. And as I started out in the beginning of this, one of the principles is hydro operations are time-based and rate of change. And so the sooner you start things, the sooner you start getting after it, that gives you freedom. And so by having this stuff available that we didn't have 10 years, we're now in a position, instead of being asked, what are we going to do? We're in a position that this is what we're going to do and why. And then coming into Monday, if this had bowed out, and I know I watch the scientists and they say, well, you can't trust, or what's the accuracy of the forecast going out 5 or 6 days. In this particular instance, this is still valuable in that, is it physically possible? Is the physics there that would support this kind of action? As opposed to, you're not going to see this in the middle of the summer. And so that has value. And as this intensity gets larger, okay, we're on the right track. Let's keep going. Now, setting up the rest of the next 3 days, I throw this in there just to show the magnitude and how fast things can get away from you. On the 2nd, a Monday, still a holiday for basically everybody, 23.2 inches for the next 16 days. Tuesday, 28, Wednesday, 37 inches of rainfall. Now, we only get 36.05 for the entire year on average. And in fact, I had to go to this outfit for this particular graph so I could get the number. Now, you come back in and you say, well, that we didn't get 37 inches. That'd be correct. We got 20. And that's not the point. The point is that this is in the forecast. It's physically possible. And with what we know, how are we going to react to it? Now, this timing here, this is the Don Pedro elevation, the blue line. The green line is the releases to the Tuolumne River. We started making those releases 15 feet below the flood control space. And again, put your policy hat on. You've come off of 2000, a 4-year drought, and the technical people are saying we're going to start flood control releases. We're going to start making excess releases before we get to the flood control space. But if you have the right tools and the right information, well, of course you're going to do that. Why would you not do that? Now, because we started that early, if we had waited, these humps here would have been a lot higher. And in fact, on both of those humps, the rainfall that was forecasted, we actually were going to hit elevation 830 3 times. They backed off. But that's not the point. The point is we started and we were in a position to absorb those if they in fact came about. The green line is dropping down because of our flood control requirements at 9th Street and Modesto, which is below the Don Pedro Reservoir. We have to bring the releases down so as to maintain no more than elevation 55 in Modesto, which is about 11,000 CFS. Our flood control requirement is 9,000 or non-damaging flows. So we we have maximized these releases, and based on forecast, and you've heard about forecast informed reservoir operations, the federal projects, I think that's more applicable, the terminology. Since 1997, because of this dynamic, we've had to incorporate forecast in our operations. So being a public agency and in charge of our own flood control space and reservoir, we have a little bit more flexibility than others. But the point is that we've incorporated forecast in our operations. We released the maximum amount of water we could under the flood control paradigm. If we had not started on basically the 2nd of January, started ramping up, the amount of water from that point to when we actually would have done it normally would have been released on the peak when the reservoir hit elevation 830. We would have gone over what we did. Now, coming into the February period, setting up in February, the forecasts are coming in, we see what's going on, we're doing the modeling. And when we started out that morning, it looked like that we were going to put 30,000 CFS into Modesto based on the modeling. And so and we were working with the Corps of Engineers hand in hand. And we reached a point up there where the reservoir was moving up pretty fast. Based on the forecast, we wanted to slow things down a little. So we went to 18,000 CFS, knowing that that was the first step to get to 30,000 CFS. But in the meantime, the CNFRC's forecasts were dropping, the rain had stopped, we were doing our own forecast. And immediately the forecast was saying, actually what you need to do is just maintain 16,000. So even though we went up at LaGrange to 18,000, we dropped it back down. The channel at 9th Street, the river from LaGrange to 9th Street absorbed that 2,000 CFS additional peak. And the river never got above 16,000 CFS. It was also being driven by the flows coming in on Dry Creek. Now, I want to come back to that graph. We filled the reservoir. That's a visual from probably at about 1,000 feet. That's a picture of the spillway. Water didn't go over the spillway. We kept control over it. We worked with the Corps hand in hand, and this is the first time that this has been done on this project, where we opened the center gate, kept it going while the reservoir was below elevation 830. And so we're maintaining 16,000 CFS here. The two gates on the outside are closed. And we ultimately floated that reservoir up to elevation 829.74. Our operational max in the summer is typically 829.64. The reason is you can't have water coming over this gate. That's 30 feet down below, by the way. It's probably kind of misleading. But the point is, we can't get to 830. You can't have water coming over the spillway. We can get as close as we can, and the wave action, we're kind of watching the wave action there. Getting back to the trust between the policy people and the technical people. So we floated the reservoir up there. I asked him, I said, well, I can cut the releases at the powerhouse and probably move that up another 1/10 of a foot. And I don't know if you can see it here. You can see where it's kind of wet, and it's kind of probably an inch or so below the top of there. And the comment was, no, we're comfortable. And I said, no, seriously, it wouldn't take much to do that. And again, that's a 15,000 acres of surface area you're going to move up by an inch. And the final response was, no, we're happy. So that's very important in that everybody's on the same page. Everybody's comfortable with what's going on. The reservoir's full. you're telling the public we've maximized the storage and the releases going down from the reservoir have been reduced as much as possible and in a controlled fashion. Now, going back to this slide here, so we've filled the reservoir. We've got the center gate open. And the flood control manual, it's very specific. You can open that flood control, that gate, when the reservoir elevation is 829 or higher. But below 829, it has to be closed. And so we were talking with the Corps, and I think it's a design issue. And they said, when that reservoir goes below 829, you're going to have to shut that gate down. But the local constituencies below us, on one hand, when you start to get in these situations, immediately everybody's saying, don't flood us out. Make sure that you don't do what you did in 1997. But when they start to get the information on what's going on and how things work, then there's an immediate change of tone. Well, wait a second here. You guys need to release that water and get it out of there. What happens if it starts raining again? So I called the gentleman up there at Moccasin who had been storing some water because it's all a team effort. They had filled their upper reservoirs during this event, and now everybody's full. So in an ideal situation, you want some reservoir space. So how are we going to do that? So we worked with Jenny Fromm, and I can't say enough about her on this subject. The inflow is dropping, so in order to keep the reservoir going, I asked them to release the water that they'd stored in those upper reservoirs down onto us. And if you can put that in perspective, so you're making releases through your spillway, you're full, and you're asking for water to be dropped on you. Now just think about that. Well, by San Francisco doing what they did, we held the reservoir at about 829 for a week. We kept the releases at the spillway going for a week, 16,000. There was no damaging flows. There was some farmland that was wet. Everybody was happy. The people clear down to Tracy were happy. We were creating space, and then we brought the reservoir on down. Now, through the forecast, we maintain this constant level in the river. And if you'll remember in the 97 graph that I showed, there's two issues here. We brought the river back up, not a lot, but it's a problem. We brought it all the way down and then we brought it back up. And we didn't fill the reservoir. Now, back in 97, we said, well, we didn't know if we're going to have another event like this. And so we were taking precaution. But if you're going to use that method or a thought process, you never would fill the reservoir. So you want a nice level flow. And ultimately, this curve here is kind of like a football throw. What happened here, though, we're using the model. We're using all of the models, using all of the data from DWR, CNFRC, whatever we get our hands on. That's just what you do. And so the reservoir starts going up. We start bringing it down. The problem was that the forecast. Now we're in May. Now this graph here was actually produced by DWR. And before I go any further, I want to make very real clear. Everybody is working to the common good. I'm hypersensitive that this stuff will be taken out of context, and somebody say, well, John's forecast is not as good as Tammy's. That each of these have their perspectives. There's reasons that they're being done, and everybody's working for the good. Nobody's out there putting a product that is not usable. So the next three graphs, I just want to kind of go into it. But the reason I show these here is, what is the state of the watershed in May with all this snow that we've had? And this was shown earlier. And you can see that from two different agencies, there's two different perspectives. This graph here is a setup for the next graph. It's the CNFRC's 5-day hourly forecast going out. And so each day they come out with a forecast. And so, for example, here on June 13th, and this funnel diagram right here is on the high side. Then you've got the average, and then you got the low side, right? And we graph this every day. Kind of looks like that. 58 years. So this is the setup to this graph. The point here is that you can see here during this period, CNFRC is coming out with their forecast. The full natural flow is writing the top line each day of the forecast. And each day they're moving it up. But the full natural flow is ahead of the ensemble. And it is also the same coming down here. The problem is we're full. You have to fill the reservoir. After coming off of a 4-year drought, you better fill that reservoir in a wet year. And the information, there's no information. So how much snow's out there? And I think Tom or Dr. Graham at Moccasin sent this to me. I'm not sure who the person is, but there is the state of the art at the time of what's up there. And I don't know. I would say you got snow 50% of the area. Now, I don't know what that means. Now, Tom did do a flight after we had brought the reservoir down, and it was about a week and a half too late. There was only one flight done that year that was due to budgeting and stuff like that. And then you've seen this graph. Olivia showed this graph to you. But this information here is invaluable. We'd had this probably about 2 weeks earlier. We'd have had more of the curve that we wanted. And then again, the ground plot. With this kind of information, you know exactly what's up there. And so now you've got some truth or a stake in the ground on what's going on and how does the other calculations and models set up. Now this is on the wet side. The dry side, which is the opposite, we had some storms coming in, shoved us up into the flood control space. But for these storms that have been a critical dry year, we're rocking along. We get to about April 25th. We're keeping the core in touch. I don't know specifically. My feeling is that, and yes, I'll admit, we got 51% encroached in the flood control space. And based on my discussions with the Corps, if you're east of the Mississippi, you're probably going to get looked at, if not asked why you didn't get fired. On the other hand, our flood control manual is very clear on its purpose. It is for flood control purposes because you don't have weather forecast and you don't know what's up in the watershed. Again, remember, that thing was signed in 1971. It was probably written, I feel, by about 1965. Okay, well, we do know. And so if you look at the way it's worded, well, and it is, you are supposed to use it for conservation purposes. That's the reason the line goes up. We got a call from the Corps. And when the Corps calls, you do what they tell you to do. And they said, we want you to go to 4,500 CFS immediately. So I called Jenny Fromm up and I said, we don't want to do that. And she says, well, you need to tell us what it is you want to do and why. And so we put together a report that said, we don't want to go over 4,500 CFS because there's no reason to do it. And once that's granted, and why is it not warranted? Because We know what's up in the snowpack due to the ASO program. We know that there's nothing out there based on scripts and the National Weather Service. There's no fuel out there for a large storm. And even if we saw something out there, I can drop that reservoir 1.5 feet a day. And since we went through a 4-year drought, one in a 1,100-year drought, let's hold on to it. And then after we get, if we can get that granted, then what we want to do is go down to 1,100 CFS. The next day, Jenny granted and we had some construction going on some bridges and some levee maintenance and stuff. The Corps the next day said, do not go above 4,500 CFS. And we'll get back to you on the second request. And the following day, they said, go down to 1,100 CFS. I would not have put that request in, but for this information, because if you don't have it, how do you know what's up there? And as soon as you ask to do something and think, well, my feeling is that you're going to find out real quick it's the opposite. Anyway, to wrap it up, this information, this discussion that hopefully I haven't butchered too much, this is a discussion that has involved many an organization and everybody is being touched by this. So this ASO, to me, this is one area of a large group of people, information, systems, programs, and this can be leveraged for other modeling programs, for calibration and accuracy. And it's just not set up. It's kind of like looking at a satellite infrared satellite photograph of some storms in the Pacific. TID doesn't have the wherewithal to fund it, much less the expertise to fly a rocket, on and on and on. So the federal government needs to do that. Just as the California Snow Surveys program is run by the state of California and the CDEC, when we get into wet conditions, it's almost impossible to get on that CDEC because everybody is looking at that for whatever reason. So I think we've all talked about the benefits. I can't say enough. We've already demonstrated very easily some low-hanging fruit. And with that, I'll wrap it up. I don't know if I'm over or under.
Wes, you're spot on for as long as you want to talk. So I really appreciate that. Do we have any questions here before we go to break for Wes? Pat, I've been trying to send a reply to your question, which I have to hand off to my colleagues, but I was trying to listen to Wes as well. So I'll send that into the we'll send that into the Q&A window.
So we have 2 hands up. Scott Havens was first, and then Peter Worcester.
Did we free Scott?
Oh, maybe Scott put his hand back down. All right.
Took his hand down.
All right,
Peter.
Well, I met Wes in, I think, at the 2017 workshop, and I could tell what a treat it is to hang out with Wes. So I always appreciate his observations. I didn't realize he had a law in his background, but I knew about the physics. But let me throw some observations as someone who represents a community that is the environmental community that is folks like my colleague Martha Davis and myself. We see a lot of benefits, of course, to the ASO program for environmental purposes. I mean, at least in the Mono Basin, San Joaquin is kind of 6 of one, half a dozen the other. There's some really good things about it, but the river is may lose some of its water. But here's an observation I want to make. We all know the benefit for water supply management. Some of us know we see on balance, it's good for the environment. But it's so, as we talked yesterday, we need to make a better case for all the different people who will benefit in the state. And I know we're doing that, and that even the Creek Fire is really spurring better relationships. But my advice would be really get that act together, and in the sense that it's so overwhelmingly positive for obviously water supply agencies, whether it's ag or urban, it overwhelms the other part of the conversation. So the legislature is going to be a little like, well, if it's so gosh darn valuable to you, why should we pay for everything? And I don't know if this is making sense, but it's you gotta find that broad benefit for one, recognize from and actually help the environmental community show how it is on balance a benefit, because there's some negative impacts to the downstream flow if it's all going to be diverted for Sigma storage. But on balance, help us, I think we can work together to show, and I think you're going to be in a better position to show and work with all the forest people, the Liz's, and all those people. And I think you're going to be in a better position to the next time you go to the legislature. I've been trying to, work with Friant and other folks like this to and I know they recognize the need to broaden the message, but the more you say how essential it is, and it is from a water supply standpoint, the more I think some of the legislature might go, well, then why aren't you, paying for it? Which, you obviously have been. But so I just wanted to, Wes, get your reaction, because I feel like Wes is someone who we all can work together to make that case. But I just want to put that out there and see, Wes, am I making sense?
No, you're making complete sense. And if I was an elected official, I'd do my due diligence and ask the same question. But there's a greater good. And I not to be too flippant, I think I used my example last time. When I get into a bind if I'm paying for the program, then I'm paying to get what I need and then get on to the next crisis. And if I fly the program in February and I only have enough money for 1 8-hour flight, I'm probably going to talk to Tom and say, hey, can I get 4 flights out of that? I just want you to fly a big X right over the watershed. And I'm going to, so you say, well, what does that do for you? Well, if I've got 17 snow course measurements once a month, and Tom flies that airplane over at 20,000 feet and through 1,500 square miles, how many points on that watershed can I get? And I'm making this up to see what sticks. I'm going to take that and put it in MATLAB. And I've probably got millions of points more than I would with the snow course measurement. And based on his initial flight in February, I probably can come up with some sort of extrapolation. Now that half-ass discussion or work, and it is by definition half-ass, is that what the state, everybody and their brother is going to needs this information? If you're going to adapt to the climate adaptation, isn't that what the scientists are saying? How are you going to do it if you don't have a complete understanding of the foundation of which all of this stuff's working? And there's a higher order of need. Yes, I need the data. It just solves a bunch of problems. I can communicate. If I've got this information, I know what we're going to do and how we're going to do it. I'm going to communicate to the law enforcement, Office of Emergency Services, the fire department, say, this is what we're going to do, and this is how you're going to save money by retasking your resources to where they're not needed. You don't need to do it on the Tuolumne. So there's this greater good, and what's the there's so many subjects here. How do you if I'm doing the program, I'm going to start hedging my bets. I'm risk averse. So Tom comes out and he produces something, and we live in a very complicated world. That's just what we do. And I'm thinking, man, this data is causing me some grief. Hey, can you put an adjustment factor for these reasons? Because we want to accomplish this. Well, you do that indirectly. Anytime that you're doing any kind of analysis, how you add the columns up. And you want it done in as a pure environment. You want everything available so that the way that I look at something, and for example, my team, Olivia and Jason, they're going to look at things differently. The last thing on earth you want to do is put my bias in their work. And it goes with the DWR, the CNFRC. You want to take out as much bias as you can. And so how do you do this kind of a program in an environment like the current California snow surveys that is consistent, it's dependable, you can, on and on and on. I can keep going, but there is, I really believe this, there's a higher order that needs to be accomplished. And I look back, it's very easy for me to see, well, of course you're going to do this, because I have had to operate without the information. And I know the hopelessness, just when somebody calls up and says, I have my home, which is a 8 by 10 foot trailer along the Tuolumne, is it gonna get flooded out? And all you can do is say, well, I don't know. And so it's real easy for me to say, hey, I know this is expensive. I know everybody likes to eat, but we're going to do this program. And it's going to be, if Dr. Anderson's a small percentage of what he is suggesting is going to take place, we're going to be doing this program all right. And we're going to do it to the degree that it has to be done.
I got a question.
Wes, yeah, go ahead, Joe.
So Wes, two real quick ones, sorry. One of them, I may be kicking the same old dead horse, but give it one more kick. Can you easily stick a dollar number on that water that you were able to convince them based on ASO in 2018 to keep in the reservoir, rather than, like when you got the permission to keep more water? That's one question. And kind of the second question was raised by what you just said about being risk averse. I mean, when in this world today does risk averse start looking like buying more surveys, right? Because that's risk aversion to me, right?
So I want to make sure I answer the question. So please make sure I answer the question.
Okay.
The first one, the dollar, the first knee-jerk reaction is okay, well, what's the current market for environmental water and then water for the, that's the first stage. And the second stage is, well, wait a second here. And again, I get back to how do I articulate the consternation when you're in a flood control situation? You've got the first responders, the fire department, that are responding to people, their house, their livelihood is getting ready to get toasted. And to be able to go to your constituency and say, okay, we have this under control. I've asked for the reasons here to promote this program. So what is the value of this to the public relations? And he says, Wes, it's invaluable. He says, you can't put a price tag on it. And to me, that is the most valuable part of the program is being able to assure the public your constituency, your customers, what it is you're doing. But you don't sell or buy that. Your credibility, your reputation. What's your reputation? I guess I'll put it that way. So what's your reputation worth to you? Organizations spend a lot of money on it. And so what's the reputation in the California Department of Water Resources and the Corps? I'm not putting a monkey on their back completely, but everybody working together, and when these issues do come up, having the information there, or better yet, and this is the thing that I want to get across is that in 1997 we were told this is what you're facing, and what are you going to do about it? Well, I don't even know what it means. As opposed to 20 years later, I'm waiting. I'm looking for that disaster. I see it starting to wait. And you got your iPad in your living room. I mean, I'm not being flippant here, but the technology is such that you're watching that crystal ball New Year's Eve come down at the same time you're looking at the Scripps deal. You've got that capability, and that all of a sudden that next report comes up. Yes, I see the disaster. It's a disaster if you don't do anything. But now I can do something about it. I can set some things in motion, and it's all about time. And the sooner you do that, the better. The dry end, yes. You want to stop those releases as soon as you can so that the reservoir is full. When you can fill the water, when historically you wouldn't be allowed to, and you would have been crazy to. But now, because you have information, and the manual says, well, because you don't have forecast, because you don't know the state. Well, you do know. So now you can exercise the use of the facilities as opposed to going out there building more storage. So on one hand, is ASO expensive? Well, unless you want to go build a reservoir, then it's probably not that. And the ASO with the corresponding infrastructure, the programs associated with it, on and on and on, probably are not that expensive. Did I answer the question?
Yeah, I mean, again, it's the flood that didn't happen, and how much was that worth, right? I mean, and then I just was thinking, like, where does I just run into places where risk aversion means doing it the way we used to, or doing it by the book. But when the book is 50 years old and you have new information, risk averse means something else.
So again, let me make sure I answer the question. Yes. So we could, we could leave at 5 o'clock and say, well, we don't have to worry about the river. That's what the reservoir space is there to do, is to be used. So we'll let it fill, and then we'll let it go on up, and we'll let you know what happens. There's too much money at stake. I mean, it's too easy to do the right thing. And everybody wants to do the right thing. So actually, that's a lot of work to just rely on the historic. I mean, I've been through some lawsuits after the 97. That's a lot of work. There's a lot of consternation, a lot of turmoil. And so again, having gone through that, and then the 2000, this was easy. Was that fair?
Great. So let's close this out and go to break here. I want to add a couple things on that conversation. Having come from the NASA world for the last 20 years, and looking at ASO in the NASA and the NOAA world, the way that I look at it is very much, sorry about the nail hammering out here. It's right outside the window. when you look at the satellite programs, in fact, the first spaceborne measurement of looking at the surface imaging was mapping snow back in 1960. And if you look at the measurement programs from a remote sensing basis, in large part, they are covered by those federal investments. And so we see this as an extension of the gamma measurements for snow water equivalent. I mean, those really were intended to get at snow water equivalent to constrain the modeling. And this is taking it to a far more spatially complete measurement with technology that's now available that wasn't available back then. And the last number I want to add, just based on the apples and oranges conversation yesterday about GOES. So as Joe pointed out yesterday, it's about an $11 billion program. One GOES-R. I was involved with that. So $11 billion would cover the Colorado River program of ASO in a full build out for about 1,000 years. So I think there's, and when you consider the return on investment that we've been hearing, then that seems like a reasonable path. And that's certainly playing out in some of the legislation that's happening. So any rate, we'll see. Let's go to break. And then actually, I'm all blurry and I don't have my my agenda, but we're coming back for talks, right?
Yep. So we'll have the improvement interlude with Kat Bormann.
Oh, yeah.
And then shortly after, we have 4 presentations before lunch.
So should we do a 10-minute break? Does that take us to what? 10:50?
10:40 Pacific
10:40?
time would be 10 minutes. Will be 9 minutes, but
Okay. All right. Let's call it 10:41 then.
okay.
All right. Thanks, everybody.
Okay, everybody. So let's just get it going. We've got a lot of content to get through today, but this is the third and I think final interlude that we're doing. And what I really wanted to point out today really quickly in a couple of minutes is just some of the improvements that we've been making on the post-raw data processing side. So more getting into the delivery and the products and what kind of things you can look forward to in 2021. And since, ASO Inc. has taken over the products. And so one thing that I want to speak to directly is from Evan's interlude on Monday. We had Evan, Joe, and Christina, our compute team, or the folks that do the raw processing. So they're getting faster and more reliable and more robust, and putting together a system or a pipeline that will be able to push these products out to us a lot quicker. And what that does is give us folks downstream a lot more time. And so that gives us time to do the things that we need to do to make sure that the products are robust before we deliver them, and to do all the things that we need to do, like, for instance, you can see here, the first update to the model, as in we fly, we get a snow depth retrieval, and the model's already been running every day or every couple of hours. It's been running up until this point, but the model doesn't really know where the snow is at this point because it hasn't been updated with the ASO information. And so what this extra time gives us is the ability to be able to work interactively with our modeling team within the very short delivery window to have the snow depth retrieval made, fed back into the model. And then what we can get at the end of the model is an updated snow density with the new snow depths, with the new distribution of snow depths for our SWE product. And so that we've been doing that in the past, but it hasn't happened every single time. And so our goal is to have this happen every single time, with the first update being the most important. The other thing that time lets us do is to really dig into our relative registration and to dig into our perceived snow depths over bare areas. And so I've talked about this many times, but I really want to show you what we do. So you can see here is a composite of our CASI data overlaid onto our LiDAR data over Half Dome. And you can see that big old bare area that we've got there in the red. And we use areas like these monumental granite peaks to relatively adjust our two flights so that they're registered together, so that over that bare surface, our snow depth is 0. And so what we do is we do this all over, like thousands of points. And you can see on the right, we have our histogram over those areas of our perceived snow depth. And we have a mean, in this instance, we have a mean bias of 3 centimeters. So we go ahead and adjust for that so that we are unbiased. And we have a standard deviation of 6 centimeters. And so what that tells us is that standard deviation gives us how uncertain our snow depth retrieval is at the 3 meter scale, because we perform this calculation at the 3 meters. And so if you multiply this out, as Tom was saying earlier, I think perhaps in the Friant video, for those early starters, you can have the 6 centimeters at 3 meter scale, but once you aggregate to 50 meter scale, that reduces to less than a meter. Less than a centimeter. And so, and so now what we're doing is feeding this spread into our uncertainty products, which I'll talk about later today. The final thing I want to say is this time, with the increased speed, this time lets us look at some things like the runoff that happens in the delta between the two flights. And so you can see here we have, this is for the Tuolumne, we have, although the picture is not from the Tuolumne, I just liked that picture. We have April 13, which was our first flight in the Tuolumne in 2020, and May 7, which is our second. And you can see that the delta SWE in the ASO product here between those two surveys was about 103,000 acre feet. Now, if you go downstream and you look at the Hetchy inflows, so the area that SWE is all going to be draining to, the inflows between those two dates were 105 or 106. And so what that tells us is that we're on track and we're self-consistent. So the snow products are consistent with what we're seeing on the ground, and we have a lot more confidence. You know, and that doesn't happen all the time. Sometimes we get rainfall. The next flight, we had May 7 to May 23. We saw a 60,000 acre feet delta in SWE, but we saw a lot more come up in the streamflow, and that was at around 83. So once you factor in some very rough guesses of rainfall, you can get closer to, you know, the number that we're looking for from our delta SWE. And so we're not looking to close the water balance here with this kind of stuff, but what we are looking to do is gain confidence in our products. And so with that extra time, we're able to do all of these things with a lot more, with a lot clearer head. So not at 3 a.m. And so we feel that this is going to improve the robustness of our products that we finally deliver. I think that's all I wanted to show.
Great. Thanks, Kat. Yeah, we're really excited about the updates for this year, and also this afternoon to hear from M3 Works on their plans going forward in the distributed modeling. Okay, so let me once again find my schedule here. Sorry, I'm scattered because they decided to do construction right outside the window, and it was rattling my brain. Okay, so let's see. I am handing this off to Jeff Deems.
I am ready
to chair this next session.
Right. Yeah, our next session
Jeff,
is.
You're muted, or no? I'm muted. There we go.
Can you not hear me? There we go.
Yeah.
I have enough trouble finding the mute button. I don't need you muting me on that end. It'll really confuse me. All right. Welcome everyone to our second research application session. Got a great lineup of talks here. Our first speaker, we would like to welcome a longtime GFOP, or great friend of the program, Dr. McKenzie Skiles. McKenzie's an assistant professor in geography at University of Utah. She leads a research program investigating snow hydrology, light-absorbing particles in snow and snow energy balance, remote sensing of the cryosphere, and cryosphere climate interactions. McKenzie was an early member of the ASO team and has been a key contributor to our data product development over the years. So welcome home, McKenzie.
Thank you. Can you hear me?
Yep.
Great. I'm gonna share my screen here. Okay. Can you see the slides? Just confirmation. Okay.
Looks
perfect.
Good. Yep.
Oh, I'm on the wrong. Okay. So I'm here to talk to you today about applications for ASO Imagery, and just wanted to recognize real quick a couple of my graduate students, Joe Meyer and Matt Olson, who have contributed a decent amount to this work. And then also the early part of this presentation will feature work that I am doing with the ARS Northwest Watershed Research Center. So I just wanted to recognize Danny, Mark, Scott Havens, and the team up there. And this work is, some of this work is funded by the NASA Applied Science Program, so just want to recognize them. So I'll be talking about ASO, imaging spectroscopy, and snow albedo products. I'm going to start with product assessment and validation, and then go into incorporating snow albedo products into snow energy balance modeling. And then I'll close today with just a few slides on some work that my group has been doing using the ASO RGB imagery and photogrammetry, and comparing that to LiDAR snow depths. Okay, so unfortunately I have had another event this week, so I haven't had much time to sign on and listen, so I don't know how much has actually been talked about in terms of the ASO imaging spectrometer retrievals, but I just wanted to put some maps up here for the Tuolumne and for the East River, showing the primary retrievals, which are grain size, radiative forcing by light absorbing particles like dust or black carbon, and then we combine those two products to come up with a broadband albedo. And I'm showing products, additionally an RGB color composite, which is just a really nice visualization that can come from the imaging spectrometer. And just to show you what kind of data comes out of the CASI imaging spectrometer that's aboard ASO, it captures the visible and near infrared portion of the spectrum. This is kind of a standard snow albedo spectrum that I'm showing here across the full solar wavelengths, and then the portion of those wavelengths that are covered by the CASI. So it's the portion of the snow reflectance where most of incoming solar is present, and the portion of the spectrum where the snow albedo is impacted by light absorbing particles. And then we also capture part of the spectrum that's controlled by snow grain size and ice absorption. So we gather enough information from the imaging spectrometer to map both of these snow properties as well as broadband snow albedo. So how do these products actually look? There was, during NASA's SNOWX project in 2017, an overflight of ASO where we were in the field collecting field spectrometer measurements, and this allowed us to validate some products from ASO. And what I'm showing here first is grain size retrieval, and we compared the ASO grain size to field measured grain size in two parts of Senator Beck Basin. And what we found was that this flight was for new snow. So if you look at the distribution or the histogram of grain size, it peaks around 250 microns, which makes sense for new snow, relatively small grained snow. And then two parts of the basin, sort of lower elevation and mid elevation, we find that the errors are relatively low compared to field spectrometer measurements. The highest errors we were getting we're around 30 RMSE for effective grain size. And so that's really promising for grain size. And then if we move to spectral and broadband albedo, here are some maps showing Senator Beck Basin and where we were actually measuring these transects and broadband albedo measurements. And on the right side of the screen here, I'm showing a comparison between the CASI and ASD measurements, which is the field spectrometer. It's kind of a standard for high quality spectrometer measurements. It's used for ground validation of remote sensing products, not just for snow, but for all sorts of applications. And we found approximately a 5% error across the full visible near infrared wavelength range, which is decent. And if we look at the broadband albedo, we can break it apart into different ranges. So the visible, near infrared, and broadband. And then what we do for broadband is actually extend out the CASI wavelengths to the full solar wavelengths using modeling and radiative transfer modeling. And we find that the match is pretty good, falls really close to the 1-to-1 line. So this gives us confidence in these spectrometer products and that we can use them for downstream purposes. So if you're listening to this, you might be wondering, you're really signed on to this because you care about snow water equivalent. So why should you care about albedo? And that is because snow albedo controls the rate of snow melt in most snow-covered environments. And what I'm showing here is that you don't have to pay attention necessarily to all of the lines on this plot, but that the red line, net solar, is closely traced by this black line, which is net flux, or the energy available for melt. So what that shows us is that the other energy balance components kind of balance each other out, and snow melt, or the energy for snow melt, comes from net solar radiation, which is determined primarily by snow albedo at the surface. And everywhere that albedo is actually measured in snow-covered environments, this relationship holds true. So we know that irrespective of latitude, snow albedo is really a critical controlling component. If you want to know how much water is held in the mountain snowpack, you also are probably interested in when it's actually going to start melting out and how fast that water is going to be coming. And albedo is a critical part of that equation. So then, the next question you typically get is, can't my model just handle albedo for me? Do I actually have to be measuring it? Well, the answer to that is definitely yes, because models are still using a time since snowfall decay curve that was formulated in the 1970s and hasn't really been updated since. So what I'm showing you here is modeled albedo in blue and measured albedo in orange. When it drops really low, that's when there's no snow present, but up here there is snow, and it's showing a much more rapid decay for actual measured albedo than is captured within the model. And what I'm showing you here is for iSnowval, which is a model that's probably most people on the call are familiar with because it's used by, or previously used by, ASO. And it's kind of an extreme example because we are measuring, in this instance, snow albedo in a really heavily dust impacted environment. But it holds true for a lot of places that we look, that modeled snow albedo just cannot capture what we're measuring. And I just wanted to show another example that's not snowval. This is actually Wharf, and for the same area, we see the exact same thing. So modeled snow albedo and land surface models also cannot capture what's being measured. So what we wanted to do then, my group is really interested in being able to model, accurately model snowmelt timing and magnitude. And if we can't get albedo correctly, we're not going to be able to model snowmelt timing correctly. So we wanted to take ASO snow albedo and build it into an energy balance model to update albedo within the model and see how that impacted snowmelt timing. So these are results for Senator Beck Basin, where we basically scale modeled albedo to a measured albedo from ASO. And we do it, it's spatially distributed. So every pixel is updated and scaled, and then we let the model run forward in time. And there's a lot going on in these plots, but the take home point is if you accurately represent albedo, you get snowmelt timing correct. If you don't accurately represent albedo, you miss snowmelt timing by up to 2 to 3 weeks. So what's more fun to watch is a video. So let me just play a video here. On the left-hand video side here, there's no albedo updates. And then on the right-hand side here, there are albedo updates. And you can see the plot running forward in time for both net solar radiation and snow depth. And this is the interesting part. When you don't have an albedo update, you keep snow around for too long because it's just not absorbing enough solar radiation.
McKenzie, will you show it again?
Yes.
Thank you.
And if anyone hears any weird noises in the background, I just got a puppy, and so she's whining a little bit. So yeah, so this is the end of the season. And that's really the stark contrast there is we just keep snow for far too long without an accurate albedo. So this was really promising for us because we are, Senator Beck Basin is a really nice place to do testing. There's a really high quality in situ measurements that go on in that basin, but we want to be able to scale up past this really heavily dust impacted basin. It's also relatively small. And so if we kind of move up to the next scale, I have a project that will be running iSnowbal over, eventually we'll get to the point where we're running it over all snow dominated watersheds in the upper Colorado River Basin. And where ASO comes into this is that there really is no other validation data set that we can rely on because it's hard to compare remote sensing data to in situ point data. We really need spatially distributed data in terms of both snow albedo and snow depth in order to validate what our sort of broader scale model is outputting. But the way that this is going to work when we scale up is that we'll actually be taking snow albedo from MODIS and incorporating it into iSnowbal, which is being forced on the meteorological side by the high resolution rapid refresh model. And this is just one example of an output over the East River watershed in Colorado, where we're currently comparing to ASO flights. And again, a video here. So this is water year 2018 over the East River watershed. We have a full water year run for 2018 and 2019. And it's very exciting that we've gotten to this point and we're at the point where we're actually comparing it to ASO data. And the next step will be updates. Because we have flights in the East River watershed from ASO, we'll be able to test snow albedo updates in this basin as well as compare to the LiDAR snow depths. So that is what I have for building ASO albedo into models. And I also wanted to quickly touch on the work that we've been doing with the ASO RGB imagery, another somewhat underutilized ASO data set. So I'm just the champion of underutilized ASO data sets, I think. But what we do with the ASO RGB imagery is that we run it through a software for structure for motion photogrammetry. And the way that this works is basically it's matching multiple overlapping pictures to reconstruct 3D structure from 2D images. And the camera that's built inside the LiDAR is really high quality. So I'm showing some images here. This one zoomed out, and then this one is zoomed in, showing how well you can actually see the cars that are parked here. And this was actually a day that we were doing field work in this area. And
I see my truck.
Yes, that is Dean's truck. We're spying on Dean's here. So the quality of this, I mean, this is from a plane. You know, it's like high above the surface. Really excellent quality imagery. And this is the flight that I'm going to be showing. So this was a SNOX flight. It was flown in a double overlap pattern instead of a single overlap pattern. And the frequency of the pictures were every 5 seconds. And so there's a lot of overlap between images. And I think I forgot to mention it's an 80 megapixel camera, so it's nice. And when we feed it into the photogrammetry software, one of the outputs, just like LiDAR, is a point cloud. And I'm showing the dense cloud here. It has about 40 million points. It's dense enough that it basically creates a surface that you can visualize what you have flown over. And then here is the geo-referenced orthomosaic, kind of just really nice imagery. And then here's the DEM. So we compared the DEM from structure from motion to the DEM from LiDAR. And really the intent of this comparison was to see if structure from motion could capture surface elevations accurately over very bright snow surfaces, because there's not as much contrast over bright snow surfaces as over other surfaces. And we found that structure for motion did a very good job of capturing surface elevations relative to LiDAR. And you might notice here that we masked out vegetation. We were really focusing just on snow surfaces, but vegetation is an established issue for structure for motion, because in structure for motion, you can only reconstruct what you see. And photos can't see through the tree canopy. And then moving up, we've moved up from just snow surface elevations to snow depth. And this is it back again in the East River watershed. And we're comparing structure for motion, snow free and snow on, to LiDAR snow free from snow on snow depths. And what we find is that it does a decent job, but that it misses some areas that are captured by LiDAR, particularly shallow snow depths. But if we look at the total distribution of snow depths, they compare pretty well to each other. And if you're really interested in this, I could go into more of the details of what's being shown in these scatter plots. But I think the take home point here is that our highest reconstruction errors are in vegetation, shallow snow, and very steep slopes that are steeper than 55 degrees. There's not a ton of snow up there, but we do have difficulty mapping snow at very steep slopes. None of this is groundbreaking necessarily. Previous studies have also shown that structure for motion sort of struggles in these areas. But I do think an important outcome of this work is that where snow depth is mapped by both methods, the snow volume agreement is almost exact. So where structure for motion can do well, it agrees well with LiDAR, but it's not perfect everywhere. Okay, and I will end there. Here's some references and some actual field snow albedo measurements, which was one of the best parts of my job. Recognize some of my funding sources, DOE and NASA, and I'll take any questions if there are any.
Awesome, thank you, McKenzie. I thought Gus had his hand up, but it looks like he put it down again. Gus, go ahead and raise your hand again if you want to ask a question. One just popped in from Jeff Dozier. Jeff, do you want to ask that, or should I just read it? It's a long one. Can you see it, McKenzie?
I can read it, yeah.
I'll read it for everyone, and then you can respond.
Okay.
Ann Nolan introduced the idea of estimating snow grain size from spectroscopy using the scaled absorption depth of the signal around 1030 nanometers. Your graphs of CASI versus ASD look like scaled absorption depth of the two instruments look different. CASI value smaller, so grain size smaller. In situations where albedo degradation mainly results from dust, this difference probably doesn't matter, but in situations where snow is clean and albedo degradation mainly results from grain growth, it would. Your thoughts? What's the signal to noise performance of the CASI in the range beyond 1,000 nanometers?
Great question.
That's a thesis defense question right there.
Yeah. Well, maybe I'm glad Dozier wasn't actually on my committee. But I would say that there are the lowest signal to noise ratio is I guess maybe I'll say the out in that longer wavelengths in the near infrared, the signal to noise ratio is not as good as it is in the visible for this CASI instrument. And one of the ways that we try to get around that is we don't actually use, when we're doing the grain size retrievals, we just do a spectral slope. So we use one side of the absorption feature instead of the whole absorption feature because it is pretty noisy. And at least initially for clean snow, the comparison looks pretty decent. I will say that we haven't done this in a ton of different snow environments, so that would take a little more work to fill in our understanding of that a little bit deeper.
Let me add to that. We are working toward bringing in a V-SWIR imaging spectrometer into the ASO wheelhouse. Probably not every platform will have one, but we're planning on having at least one, and that will then have a considerably better signal noise ratio in that near IR part of the spectrum. So then we can start hitting it with the various metrics, what McKenzie and her team have been doing, and likewise the integrals across the feature. And it looks like there's another question and another new puppy. And McKenzie, great talk, and I'm really excited you got a new puppy.
Thanks. Do you want me to answer?
From,
okay, go ahead, James.
Question from Bob Krugmeyer. With the wildfires currently in play this year, how much impact on albedo do you think we might see as a result?
This was not covered, so I don't want to say that wildfires don't ever impact snow, because they certainly can, and they can impact perennial snow cover in the summer. But there is sort of a temporal mismatch between when we get our primary seasonal snow cover and wildfire season. So you can get deposition of ash and dust onto snow, and we've shown in the glaciers of the Pacific Northwest that has an impact on glaciers, but to date, it hasn't impacted the melt season, the seasonal snow melt season. And we know that wildfire season is shifting and starting earlier every year, so that might change going into the future. But so far, it hasn't been an impact on the main snow melt season.
I'll also add to that with the creek fire still burning over in the San Joaquin, the elevational reach of that has been up to around 10,000 feet. And so some work done by Ann Nolan's former graduate student, Kelly Gleason, who's now a researcher in her own right, showed that for a few years after fire, the sloughing of charred tree mass onto the snowpack can actually have a pretty substantial impact. So so it's going to be really interesting to have those data over the San Joaquin this year, and over into the Kings as well, in those considerable snowpack areas where there is that charred forest. So we'll have more of an answer. Bob, come back next year. We'll have
I'm glad you brought that up, because another impact that, rather than just the direct albedo impact, is we just had a paper out where there was a burnt down snowtel up in the Pacific Northwest, and we were able to compare the sort of pre-burned period to the post-burn period, because they actually rebuilt that snowtel. And we were able to show that post-fire, snowmelt is faster because the canopy is gone and you get a shift in your snow energy balance regime. And so there's definitely more impacts past just this sort of direct snow albedo impact.
Awesome. Good stuff, McKenzie. Thank you so much for that. We will move on to our next speaker, who is Dr. Kristoffer Aalstad. He's a researcher at the Department of Geosciences at the University of Oslo. His interest in data assimilation in reanalysis and cryosphere system models dovetails nicely with ASO data and our research support interests. And looks like he's been doing some work in ASO's backyard in the Mammoth Lakes Basin. Kristoffer, take it away.
Hello, can you see me?
Yes.
Yes.
And hear you.
Okay, super. I will try to share my screen. Can you see the presentation?
We see a global map.
Oh yeah, that's good. Just
okay.
I kind of skipped spoiler. Okay.
There it is.
Great. Thanks a lot for introducing me, and thanks for inviting me to speak here. I'm really excited to work with the ASO dataset that I've been playing around with for some years. So the original title of the talk was Testing Ensemble-Based Snow Reanalysis in the Lakes Basin using the ASO. But I thought it would be more fun if I called the talk There and Back Again, from the Arctic to the Sierra Nevada. So that's a reference to The Hobbit for those that don't get the reference. I would like to thank my co-authors for this work. This is work I did as part of my PhD, but as often happens, I haven't had time to publish it yet, but we're hoping to submit this paper soonish. So I mainly work in projects related to permafrost. The thing about permafrost is we have kind of an idea where it is and what state it's in, but the kind of state-of-the-art map for a long time was basically just a hand-drawn interpolation between different boreholes. And that's what we see here. You see this strange straight lines, and that's not how nature looks at all. So because of this, in 2015, my supervisor and now boss, Sebastian Westermann, he got a project funded where he wanted to try and use satellite data to constrain permafrost models using data assimilation or inverse modeling. And this is one of the first outputs of that project. And then you get maps that look like this. So permafrost, I forgot to say, for those that don't know, is permanently frozen ground. So ground that's been frozen for 2 or more consecutive years. And in this map, the areas that are in the blue shades, so below 0 mean annual ground temperature, are estimated to be permafrost. This is kind of a fusion of meteorological reanalysis data set and MODIS LST data into a very simple permafrost model. Since then, this approach has been made global in the ESA CCI permafrost project. This is done by my office mate, Jaroslav Obu, in this figure here. And the reason, of course, that we want to study permafrost is that a lot of carbon is stored in permafrost soils. And when the permafrost thaws, some of this can be mobilized and released to the atmosphere. So actually, even if just a small fraction, which is what we think of this carbon is actually vulnerable to be released, that would still be a significant amount, given that the permafrost carbon pool is between 900 and 1700 petagrams of carbon. And what we can afford to reach the 1.5 degree target is minus 30 to 140 petagrams of carbon emissions. Yes. So a little bit about me, why I got hired in that project. I'm actually a meteorologist. And prior to working on this permafrost stuff, I was working on measuring turbulence over snow, actually. And when I started working on this permafrost project, I got more into the snow side of things. And it was fun for me to learn that the site that I worked on during my master's, so that's in the map here in the top left, it's the middlemost point from south to north. And then just north of there, this is on Spitsbergen in Svalbard. So this is very high up in the high Arctic. Very close to that site is a glacier. And according to the famous paper by Anderson, or it's not a paper, it's like a technical document. This was where the first modern application of snow energy transfer theory was done by a guy called Harald Sverdrup, who ended up in the States actually as a professor there at the Scripps Institute. I just thought this was a cool like side story. But let's jump into what I actually work on. So now I work on data assimilation. So for those that don't know, data assimilation is kind of, you can define it as just work in progress informally. More formally, it's the updating of mechanistic models. So this is then as opposed to, for example, machine learning, where you just, basically it's a high dimensional curve fitting and you learn some kind of model or some kind of regression. In data assimilation, you use a physically based model of some kind and you try and adjust the state and parameter values of that model to match the observations. So there are many related disciplines. You can also call this inverse modeling. The basic tool that we use is Bayesian inference. So then there's this famous Bayes theorem, which is equation 1 here. The most important thing about Bayesian inference is that you no longer treat probability as just a frequency, like many people would treat probability. Instead, probability is a more general measure of uncertainty. So it's an epistemic thing. It's not a real thing or a quantity of nature. Yes, this is the only math slide, I think. So this is the kind of areas we want to study. This is in Siberia. This is a Sentinel-2 image, and you see this wildfires raging from this summer. And there are all these thermokarst lakes, and from these, there's a lot of both CO2 and methane emissions. The problem is it's really hard to go and do field work in Siberia. So at least we're lucky that in northern Norway, there is this kind of landscape that's kind of an analogy to this landscape. And we have this really small palsamires, but we can use them as like miniature Siberias. So this is from the summer. In the left, you see what such a palsamire looks like. This brown mounds are what we call palsas. So they're frozen mounds of peat. And so this is permafrost, and it contains a lot of organic material and carbon. And then we have eddy covariance towers that then we can use to measure the flux coming out of this area. Of course, doing field work here, there are a lot of bugs. It's not as pleasant as being up in the mountains, but we have this nice cloudberries that you see in the far right image, which we can enjoy. And then it's not as bad to have these bugs flying around everywhere. A reason snow is important, which I try to show here, is that if we take these palsa mounds as an example, on top of the palsa mound, there will be not much snow in general, and the snow, so that's in image B. And the snow will be quite shallow and quite hard packed. That means that the insulating capability of the snow is much lower. So the ground actually gets much colder during the winter, so you're more likely to have permafrost there. Whereas on the sides of the mound, you will have a deeper, more fluffy snow. So the insulating capability of the snowpack is higher. So the ground actually stays warmer during the winter. It doesn't cool down as much. An extreme example of that is shown on the right, where you see the tops of these palsas are completely bare blown. So you can actually see this effect in Earth system models as well. And this was actually recently added to CLM5. That they made an improved snow densification, so improved compaction with wind, and then you see that the snow density increase in the Arctic. So if you look at for example, the third column here in the bottom, this is the CLM 4.5 with the specified forcing, and then to the right of that is CLM 5, the updated version. So you see that with the denser snow, you actually get a shallower, what's called the active layer. So that's how far down the permafrost is thawed every year. So that means in effect, you actually have more permafrost. And this is actually, this map that we see in CLM5 is closer to what we would expect to see in nature. So this is just a nice example of a simple process that you then put into an Earth system model and it improves it. So to get back to the snow side, when I started, I was told the hardest thing for our permafrost models and permafrost mapping is actually the snow. So I was given this data set from Siberia, and I was told, okay, try this ensemble Kalman filter and see how it works. So then I assimilated this passive microwave data, and it seemed to work beautifully. I call this a naive snow data assimilation experiment, because even if it looks like it's a perfect fit, more or less. These red dots, which are passive microwave measurements, they basically have nothing to do with what's going on in the field or the scale we would like to model snow at. And then I realized this was a much harder problem than I thought. So I started digging in the snow literature more. And then I found this really nice review paper by Jeff Dozier that says that this is actually one of the biggest unsolved problems in snow hydrology, is to know how much SWE there is. And he argues that a really big part of the solution is satellite remote sensing and a technique called snow reconstruction. As you see here, this is from a MODIS True Color Composite, and you see that the seasonally snow-covered areas match really closely with the permafrost region that I showed you in an earlier slide. But we also see that if we go from, for example, January here to August, this area of snow cover decreases a lot. So this has a huge impact on both climate and water resources. This is why I was happy to work on snow, because the snow community is actually much bigger than the permafrost community. And there's a lot more interesting things actually about snow, but don't tell the permafrost people that, then they get mad. So yeah, you see that here, these are the population centers. So you just see the importance of snow also for water resources, for example. In terms of remote sensing, there's the GRACE satellites, and from those we could retrieve terrestrial water storage, but it's really hard to decompose that into the SWE that we might be interested in. There's also optical, as you know, that has problems with clouds. On the other hand, if you can mask out the clouds and you can use the shortwave infrared, it's relatively easy to identify snow-covered areas. Finally, there is passive microwave, which I already talked about, which, at least as far as I understand, has big problems in complex terrain and forests and for wet and deep snowpacks, which is basically everywhere, as far as I can understand. The method that I ended up using is called ensemble-based snow reanalysis. It's a probabilistic form of the snow reconstruction approach. So this should say Martinek and Rango 1981 at the bottom, but it got cut. Sorry about that. So this is a method that has been around for a while. It was originally proposed in some papers in around 2006, and it's been used by Steve Margulis's group to map the SWE over the whole Sierra Nevada. I have a few papers with some colleagues where we use it in Svalbard and in the Swiss Alps, and now recently also in Lebanon. And the idea with this technique is that you use data assimilation algorithms, which are approximate ways to solve the Bayesian inverse problem. And what we try and do is we try and assimilate snow cover data to take into account that if a snowpack lasts longer, then either there must have been more snow to begin with, or there must be less snow melt in that area. So there's kind of an equifinality problem, and there are, of course, issues with snow modeling and issues with the forcing and issues with the satellite retrievals. But the nice thing is in such a probabilistic framework, you can try and account for all these different sources of uncertainty. So quickly, before I move to the ASO example, I just wanted to show a recent paper where we used a camera that we have installed on a mountain in Ny-Ålesund. So this is in Svalbard. And using this camera, we get really accurate snow cover maps with like 0.5 meter resolution, and we can use those to validate satellite retrievals. So this is how that works. We have a time-lapse photograph, and then we crop it to a certain area, we orthorectify it, and we just apply a threshold, and we classify each of the images. We have around 300 of these images, and they're now available on Zenodo if someone wants to try that out with some optical remote sensing product. They're welcome to do so. So this is an example. In panel A is this orthophoto. Panel B is the reference snow cover map. Panel C is a Sentinel-2 false color image, and then I show 3 different ways to get snow cover maps from the Sentinel-2 image. The first is just a standard normalized difference snow index threshold, and the second is spectral unmixing, and the third is actually the snow map that's, or the QA flag that's provided by Sentinel-2. And you see that that's not great, whereas the spectral unmixing we found was the algorithm that performed best. And this is kind of in line with the literature as well, which was nice to see. Here is more of the same thing. In the far right, you see that the spectral and mixing, that's SU from Landsat 8, and Sentinel-2 seems to be the algorithm that retrieval algorithm that matches the reference data best. Anyway, now to the ASO. The study area that I worked on is the Mammoth Lakes Basin. I was fortunate enough to be there for the ASO meeting in 2018 before this Corona madness happened. And it's a really beautiful area. And it's a small basin, which is nice for me because the ensemble runs that I do are relatively expensive. So for those of you that don't know, it's very close to Mammoth Lakes. This is the basin. And there's a lot of measurements nearby at the Q station that I can use to look at how well the forcing data performs in this area. So this is just an overview of the experiment. I looked into 4 water years from 2016 to 2019. The model I use is a really simple energy balance model. It's just a single layer snow model. We ran it at 100 meters with a daily time step. We used downscaled NLDAS data. The data assimilation scheme I used is an iterative version of the ensemble smoother, which is a version of the ensemble Kalman filter, where you assimilate all the observations at once, which allows information to travel backwards, which is actually what you need for the snow reconstruction problem. If you were to use a filtering algorithm, it just wouldn't work for this kind of problem. The number of uncertain parameters in this system, I have 6 uncertain parameters. I won't go into detail what they are, but I can if someone wants to ask me that later. I assimilate fractional snow-covered area retrievals from Landsat 7, Landsat 8, Sentinel-2, and then also these 2 commercial satellites, Rapid Eye and the Planet CubeSats. And for validation, we use this ASO flight. So in total, there's 15 flights, and then also Avarice fractional snow-covered area from 3 Avarice flights. So this is an example of what we can get from the Avarice flights. This is on the right is the fractional snow-covered area. To the left is the false color image. This is what Landsat 7 image looks like. We're lucky that the Mammoth Lakes Basin actually falls inside the area where the scan line corrector off issue isn't a problem. Then Landsat 8 is similar. Sentinel-2 a little bit sharper due to the higher spatial resolution. This is 10 meter pixels. And then for the Rapid Eye and Planet data, we don't have shortwave infrared bands, so we don't use spectral and mixing. Instead, we just use a binary thresholding technique. That's why you just see this white and black and no gray areas. So this is the Planet data. This is just a brief validation that we did. So on the x-axis is either ASO fractional snow-covered area at 100 meters resolution or Avarice fractional snow-covered area. And then we have the measurements or retrievals from satellites. And we see that it's not perfect, but the RMSE is around 0.1 for most of the retrievals, which is good enough for us to do data assimilation. We don't need perfect observations to do data assimilation. These are some results for the basin averaged quantities. So the model is run at 100 meters, and then we just aggregate up. It's around 3,000 grid cells. In red, we see the prior spread of our model. So this is before doing any data assimilation. In the diamonds, we see the ASO and Avarice data that we use for validation. So this isn't assimilated at all. And then the satellites are the satellite retrievals are the circles. So you see there are actually a lot of satellite retrievals in one season because this basin is relatively cloud-free compared to other basins I worked on. And this new satellites, such as Sentinel-2 and also this commercial Imagery, really helps to fill the gaps in the Landsat data, which is really nice. And you also see that the snow water equivalent, which is what we're interested in, the blue, which is after data assimilation, is much closer to the independent validation data. So this looks like it's working well. Here is the same thing, but just as a scatter plot. In the left is the fractional snow-covered area, and the right is the basin mean snow water equivalent for the 15 ASO flights. This is a logarithmic axis on the right. Right. So this is an example of the spatial distribution of SWE. So the left columns show the prior SWE for 4 flights. And in the middle column is the posterior. So this is after updating with the fractional snow cover. And finally, we have the ASO validation data. And to the far right, we see the error histograms. The data simulation seems to be working as it should, with the posterior outperforming the prior. Especially in 2017, there is a long left tail to the posterior histogram, and the errors are considerably bigger, but that's also because this was a really high snow year. So some more interesting results maybe, or actually this is maybe not that interesting. Here we see the effect of assimilating multiple sensors compared to just using Landsat 8, which is what is usually done. When we use all these satellite sensors, we actually get a decrease in RMSE of 27%, and we get a mean relative increase in the correlation coefficient of 14%. Both of these are significant at the 5% level for those that care about such things. And then this is the more interesting slide, I think, at least from a scientific perspective. So the way we relate what the model predicts, which is basically SWE, to what I observe or we observe from satellites, which is the fractional snow cover. To do that, we need a snow depletion curve. And we use a probabilistic snow depletion curve. Usually what's been used is a log normal snow depletion curve, where you assume that the subgrid snow distribution at peak SWE is log normally distributed. In Norway, we've had some success also working with the gamma subgrid snow distribution. So I just wanted to test what the effect of that would be. And it seems like, at least for this basin, the gamma distribution seems to represent the subgrid snow distribution more accurately, at least given this validation. Just some data assimilation stuff. I actually compared a bunch of different algorithms. So on most of the x-axis here is the number of ensemble members. So this summer, almost no one was using the cluster, so I could run a lot of model runs, which was nice. And we see in blue that this ensemble smoother with multiple data assimilation, which is the algorithm that we mainly use, seems to perform best no matter how large your ensemble size becomes. So this is important because this algorithm called the particle batch smoother, which is a version of the particle filter, is currently the algorithm that's being most widely used. And this suggests that maybe it's a better idea to use this ensemble smoother, even if it is a little bit more computationally expensive. One final slide. All of these data assimilation algorithms are actually approximations of Bayesian inference, and it is possible to use even more accurate techniques, such as a Markov chain Monte Carlo. This is much more expensive, though, because you can't run your ensemble in parallel. You have to run one ensemble member after the other, and you usually need around 100,000 model runs for each grid cell. So here we see the improvement of going from this ensemble smoother with multiple data assimilation to the much more expensive Markov chain Monte Carlo algorithm. And of course, there is an improvement, but I would argue that it's not that huge. So maybe for the applications that we have in mind in the future, where we want to scale this up to maybe global scales, this is encouraging. Of course, this is a really small basin, so it's hard to make any kind of extrapolative arguments from that, but we'll see. Yeah, finally, I wanted to show a fun example of using ASO for teaching. So this is an exercise that I made last week for some master students. And the idea was to use the ASO data to try and make an optimal placement of sensors in the field. So this is, of course, highly idealized, where we randomly distribute 100 stations around the Mammoth Lakes Basin. And then we see which distribution of stations allows us to reconstruct the mean SWE in the best possible way using a regression algorithm. So in this case, from machine learning. So we kind of jumped on that bandwagon like everyone else. But it's just a nice way for the students to play with spatial data and data that's actually representative of the scales that we might want to model at. So finally, just some comments about scaling this up. So I'm really excited to keep working on with ASO data, because when you look globally, there's really not that much snow data, which is both spatially distributed and representative of the scale that we want to model at. So for this global maps of permafrost, I will need to do these runs at 1 kilometer, and then using station measurements or point measurements can be problematic, as most people would agree. So I'm looking forward to maybe trying to use more of the ASO data set that's available. And yeah, because of course that's mainly in the Western US, but hopefully we can argue that if it does well there, then maybe it does well in Siberia or the Arctic. Right, just a last slide before I finish. I don't know if I spent way too long now. We got a new project funded where we use drones where we've configured the sensor boards ourselves. So this is my colleague Norbert Peart that's leading. And we want to fly multiple drones at the same time, which we're already doing. And they measure different atmospheric constituents and temperature, wind, etc. And then we want to try and use that to estimate surface fluxes, both in snow-covered and non-snow-covered areas, because this is a really big problem for eddy covariance measurements, just like snow measurements. The problem is that it's not necessarily representative. And if you want to identify methane or CO2 hotspots, then you need some way to scan the whole terrain. So it would be really cool if we are ever allowed to come to the US again to try to fly these drones in a basin where ASO has flown. So we could use maybe the canopy structure in the LES models that we're trying to run. So that's it. Thank you very much. And I just wanted to thank the ASO team for providing all this data, especially Tom Pater and Kat Bormann. Thank you very much.
Thanks, Kristoffer. While we are transitioning to Lindsay and Ethan's talk, there's one question. Utkarsh asks, he says the NLDAS forcing is at a resolution of 12.5 kilometers. Do you downscale that using finer DEM data? And if so, is the DEM sufficient to capture the added complexity at finer resolution?
Yeah, so we use an algorithm called TopoScale, which is based on partly on previous work, also by Jeff Dozier, with scaling of radiation terms based on slope and aspect and so on. And then we, for the other terms, yeah, so there is a DM correction to answer that point, or a topographic correction. And then we also apply some scaling terms to, for example, temperature. So it depends. In this case, NLDAS doesn't have multiple atmospheric levels, but other reanalyses might have that. So then we can use that kind of information as well. But of course, forcing is always a big problem. Yeah.
Okay, great. Thank you. That was a wide-ranging body of work you've done there, and happy to see ASO included in there. We unfortunately had our 11 o'clock speaker had to drop out, but it buys us a little time in our schedule, so we'll move on to our next group, our next presenters. That's Drs. Lindsay Bearup and Ethan Gutmann. Lindsay is with the Bureau of Reclamation's Technical Service Center. She combines high-resolution modeling and field measurements to explore complex interdisciplinary challenges in hydrology, forest ecology, and chemical cycling. We've spent some time in the field in the East River together. And Ethan is a hydrologist at the Research Applications Lab at NCAR, where he uses a multidisciplinary approach to studying hydroclimatic questions in mountain systems across the globe. Both Lindsay and Ethan are regular collaborators with the ASO team in multiple venues, so really pleased to welcome them here today.
All right, thanks so much, Jeff. And I'll kind of do the bulk of this presentation, but I'm hoping Ethan can jump in with any Q&A. So let's get that going. All right, stop me if that's not working, but otherwise I'm going to plow on. So today I'm going to talk about a little work funded by Reclamation that sort of generally is titled Exploring the Use of ASO in Streamflow Forecasting. So as Jeff mentioned, I'm Lindsay Bearup. Ethan Gutmann's also on the call and responsible for a lot of this work. Tom Painter, of course. Andy Wood at NCAR and Kostas Andriatis, who's now at UMass, are all collaborators on this effort. Like I mentioned, funded by Reclamation, but a lot of the heavy lifting is being done at NCAR. You also see Jeffressi's logo on there for our contracting gymnastics. But ASO is there at the bottom because that's really where we were going with that. So the motivation for this work really comes from the questions we've been talking about throughout this whole meeting. You know, we're merging advances in technology across hydrology. It's not only observations, but it's also modeling. And we've heard great examples of all of these approaches over the course of these few days. And those are the types of conversations that I think are kind of ongoing and really motivated this work is how do we do that? And so where I sit in the Technical Service Center at Reclamation, that's kind of, those are the kinds of questions we get asked a lot. And there are ways to quantify. So kind of looking back at Lorna's presentation from Denver Water earlier this week, I was typing these questions out frantically because I think they're motivating for a lot of our work. You know, what is the optimal time to do flights? How many flights per year per basin are helpful before there's diminishing returns? How can the river forecast centers use these? What do they need? How do they incorporate them? And how can you correlate snow yield to within a watershed? And she had others, but those are some of the ones I captured there, and certainly the motivating questions for this work as well. And so the approach we've kind of taken to answer some of those questions is, I guess, 5-prong here. But it starts with some basic snow statistics, and that can get to a lot of the questions that not only Lorna, but a lot of the folks within Reclamation have been asking. And then we can use that to also build an ASO-like data set. You know, where everyone's working very hard to boost this data set, but the reality is to, you know, start to calibrate and validate models, we need these long-term consistent data sets. So part of our approach here is to sort of use some of these statistical approaches to kind of extend the ASO data set until it's there for real. And so we can do that also for statistical forecasts, which we will then compare the trade-offs in the long-term record of index stations to the spatially resolved data of ASO. So that's sort of the statistical forecasting piece. But all of this is moving to an ensemble streamflow model implementation and forecasting, and that's kind of what we're actively working on now. I'm going to present some of the results of the statistical pieces, but all of that's kind of being done in preparation for these model analyses and explorations, not only with building the models, but also using them for forecasting with data assimilation, which great lead in from the previous talk. And the final piece that I will kind of touch on today a little bit is this quantification of the number of ASO flights required. And I know, you know, required for what, right? So certainly as we kind of dive into it further, that's what we're keeping in mind, because it's going to be a different metric that you're trying to meet. If it's, you know, again, the Denver Water example of, you know, we need this flight now to understand how much is up there versus a seasonal forecast or many other uses that we've heard about for ASO. So keep that in mind, but we'll talk a ton about the trade-offs between the number of flights and the reductions in uncertainty. So this first piece, oh, and I should mention, we're doing all of this in the Tuolumne River. I almost skipped over it. We've talked about it so much, I feel like I don't need to introduce it at all. But obviously, this is where the record's the strongest, and that's why we're focused on that basin, even though it's not a reclamation, it's not feeding a reclamation reservoir directly in the Hetch Hetchy, but certainly the strongest data set there. So just a really high level on the statistical analyses we're doing as part of this project, or we've done. We've used some basic multiple linear regression approaches with the snow pillows to predict basin average ASO SWE. And again, this is getting at sort of being able to extend the time series, understanding how much value there are in these very spatially intense data sets for some of these larger metrics that water managers might be interested in. And we're using 15 snow pillows in the area. I understand the Hetch-Hetchy relationship usually uses 10, that same idea. And I think we actually managed to snag one at a higher elevation by going a little further. We're using 53 ASO flights, and we're focusing on 3 stations here of those 15 that I mentioned. And that's because we kind of consistently found through this leave one out analysis that that was sort of the sweet spot. So that's where we landed there. Some stations are further away, some have less snow, all of these things that may make them less suitable for these basic predictions. There's many possible combinations of stations and flights and methodologies. So keep in mind the assumptions here are going to be those inherent to linear regression, as well as, assuming stationarity. So when we think about these statistical methods, that's always something to have in the back of your mind, is what if the future is statistically different? And I will leave that out there because I think you all know that it will be in some ways. Yeah, and so we, didn't expect that to happen. There we go. I think that pretty much covers that. So just the outputs of these multiple linear regressions. The one on the left that you're looking at is basically the predicted basin SWE on the bottom from this equation, which looks something to the effect of basin SWE equals station 1 times the coefficient plus station 2 plus a constant kind of thing. And then the ASO basin SWE on the left axis. So how well were we able to do? And any application, you'd look at this and say, there's a lot of correlation there. There's a reasonably tight R-squared, a very tight R-squared if in the context of other applications. And a root means a square error of about 12 millimeters. And of course, 12 millimeters over the Tuolumne is not an insignificant amount of water for a water manager. But there's a fair amount of predictability within the system. Perhaps that being overfit, what you look to on the right is then an example of a leave 1 year out multiple linear regression. So that has a little bit of that cross-validation in there. Basically, by each year data was left out and a stepwise regression was performed on the remaining stations to kind of find the best ones. And then that regression fit was used to predict the flights on the remaining years. And so you see there by, building a slightly more robust approach to a multiple linear regression, the relationship is not as tight, and you get that rise in the root mean square error to about 27 millimeters. And so now we're talking about more water over the range of the basin, despite the ability and, the predictability that is in the system. And you can see that for certain points, that ranges off by something almost 100 millimeters. And that's an important point to make here. So, those we're looking at basin averages. If I can start this. But we all know that these basins average over many different variabilities in the snowfields. And so what we're looking at here is just that first multiple linear regression and the errors in that. And so you can see how, they're not always uniform, and they're typically not uniform over the basin. And those effects are usually the highest at high elevations. So you can see these dark areas that pop up as we kind of pan through here, being the areas that these snow-tail stations aren't able to capture, and even building relationships, between those and the spatial fields. And so again, I'll point out, the cumulative effects of these errors, that 12 millimeters I was talking about, may equate to a lot of water, and a lot of water that's sort of unknown at these higher elevations. And this motivates this move toward less lumped models that can capture the spatial variability. And the value that may be added to that for forecasting, I think, sort of has yet to be quantified in a consistent way. We have all these anecdotes and we understand it sort of inherently, but I don't think that quantification is out there. And that was the focus of this study moving forward, kind of where it's going. So I there might have been a couple more there, but I think you get the point. And that moves us into this this idea of the uncertainty across the number of flights. So what we're looking at here is basically a change in the R-squared, change in the goodness of fit for a 3-index station linear model. So we're looking at the R-squared on the y-axis and the number of flights used to generate that linear model as on the x-axis. And so we used 500 randomly selected subsets from the full flight time series, and said, how well can that type of a setup predict the SWE there? And so the mean of that 500 randomly selected subsets is in blue in this plot, these blue X's. So you see, on average, if you get out to about 6 flights, you're hitting a pretty high correlation between what you can build from a set of stations and what ASO is giving you, kind of thing. But that is obviously not the whole story. If you hit the best substation, well done. And, we have some ability to choose our flights for good timing. Again, I think that Denver water example was a great one there. They really nailed it. But, you get really high levels of correlation between our stations and ASO. But if you happen to hit the worst subset of flights, your green line in this case, and this could change depending upon that 500 randomly sampled. There was no seed set there, but you see that even with 8 flights, you basically have no predictability in the system. It then jumps again. That exact location may be different, but you're out to 15, 20 flights before you're seeing that same level of predictability just from the index stations alone, or those in situ observations. And so I'll flip that again and say, not flip it, but kind of highlight again these orange dots, because here we're talking only about the years with high SWE. And so if we pick that mean for the high, or if we look at that mean for the high SWE years only, so now we're trying to predict something that's slightly abnormal, right? If we start to think about that stationarity assumption breaking down, and these more extreme years being more common, we highlight some of these high years, and now you're only at an R-squared of about 0.8, and think of how much water that would be over the Tuolumne, and even worse in low years. So now those orange X's just jumped to being low SWE years, and we have to have 15 flights before that mean of that subset gets out to even 0.8. So the point of these is, maybe for your application, that's enough. 0.8 is not nothing, but it also may not be enough when you're having to make these critical, release decisions and operations decisions for these reservoirs and other systems. But ultimately, the goal of the study is moving toward flows into the Hetch Hetchy. And so these are probably similar to some plots you've seen before, and I think some of the managers in the Hetch Hetchy use as well. And so what you're looking at here is on the x-axis, you have snow or snow plus a percentage of precipitation. And on the y-axis, you have observed flow into the Hetch Hetchy in 1,000 acre feet. And that is cumulative from the point of the observation through the end of July. So that's why that precipitation amount is kind of critical. And you see that because on the top, you have just the snow pillows. And on the right, you have just ASO. On the bottom row, you then have the pillow plus 0.35% of your precipitation, and then likewise ASO plus 0.35 times your precipitation. So there's just a few interesting things to look at here, and this is kind of getting at that question of going straight from ASO or a set of snow tail sites or snow observation sites in the case of California to streamflow. Skipping sort of that modeling step, if you will. And I think there's one point I should make. We're not comparing to a one-to-one line here. We obviously have different units on the X and Y axis, but if we then regress, take that regression and calculate the error from this relationship, we get a root mean square error of the numbers you see here. And so kind of decreasing as we kind of increase the expected robustness of these inputs. So the pillows alone they do all right, but then we see, these X's. I'm not sure if you can see my pointer, but these X's at the higher ends of the flow spectrum here, from 1,000 up in the upper left quadrant. And that, and Ethan can correct me if I'm wrong, but my understanding is those are 2017. So, what we were just talking about here, those high flow, somewhat unpredicted years, obviously we need to include precipitation. I think it was kind of a nice reminder. So if you jump down from there, you can see that falls more in line, but there's still a fair amount of scatter in the flow when we do that. ASO, the same thing. I think from that upper right down to the bottom right, we snap that one point in line quite a bit by adding in the precipitation remaining for the season. But you really don't, until you kind of get to that lower right with ASO plus precipitation, do you really start to drop your root mean square errors to about 46,000 acre feet, which is it's better, still a lot of water. And so, ASO obviously doesn't account for the amount of water that will remain, but this gives us a nice place to start. There's investments in improved forecasting, but that, an investment in this is an investment in your baseline. And so they provide that place for these ensemble streamflow predictions to start and to reduce that uncertainty in the starting point, which I think you can kind of see the benefit of as we look at those different just statistical approaches. But we're again looking toward more predictability in the Hetch-Hetchy, or whatever watershed. Again, this was mostly chosen due to the availability of the data set. So we can think about what other products we have out there. So I just provide this as sort of context. This is the CNRC's SAC simulated flow versus the observed flows, and CNRC will tell you that it's a highly calibrated and highly manually controlled model. So you do get a good fit, and it's something we've been using for years. So how do we move away from the need maybe not interfere, but to so tightly control these models? How can we sort of build the data into this model to do that for us based on observations? And so that's where this project is going next. So the next steps in this project, that SAC SNO 17 model I just showed, was the CNRC implementation. We kind of have an offline run that we can, version of the model we can run outside of their forecasting system. And we're updating that to be consistent with basically the model that produced the figure I just showed you. And we are continuing to work on best practices for assimilating ASO data into multiple model configurations. So the SAC SNO 17 obviously being very lumped. We're using VIC for more of a distributed representation, although there are simplifications in the SNO model. And then what you're seeing on the right here is actually Andy Wood's, grabbed the tuolumne from his larger SUMA implementation, and just looking at that off the cuff with no additional calibration, there's some skill there. So we're looking to use that SUMA configuration as well. And that's nice because it allows us to look at different configurations of the model and how ASO can, best be used with different configurations. And we also hope to kind of complement what the CB RFC is doing with their seasonal forecast analysis in the Upper Gunnison with some of these approaches. So that's kind of the statistics we've been looking at just as we develop these models with the help of Kostas and Andy. And get some of those larger ensemble streamflow prediction type questions asked. And so again, I'm Lindsay. Ethan is really the mastermind behind it all. And so I'll kind of have him jump on if there's questions, like I mentioned. But I'd also be, I wanted to mention that Reclamation is also sponsoring the SWE prize competition. And the question, I heard earlier asked, how can we integrate ASO with other satellite products? ASO is a developing program, as you all know. I don't have to tell you that. And so, has some strengths, but one of its current challenges is its, spatial and temporal coverage. And so a piece of that is kind of built into this prize competition. Jeff has been so great, and many of you on the phone have been great to call into the subject matter expert team developing that competition. So it's coming soon. So keep some eyes out for it, either as a contestant or just as an interested party. And it's looking at how we can get to west-wide spatially distributed SWE basically weekly from what's out there. So I'm happy to take some questions on that if anyone has it, but I didn't want to take up too much time. And again, I'll let Ethan jump in too if there's any on sort of some of the statistical work. Thank you.
Great, thank you, Lindsay. Not seeing any questions coming in just yet. Go ahead and raise your hands. Oh, there's Gus. Go for it, Gus. You are unlocked.
Thanks, Jeff. Hi, Lindsay, and thanks for the presentation. Really interesting stuff. I was just curious, so to better understand the statistical analysis you did, those were 53 flights over, I presume, is that like a 4 or 5 year period or something like that? And then also just wondering, are the dates of those flights centered mostly in the sort of post peak, or as far as snow goes, or is it distributed over the entire winter?
It's distributed over the entire availability of the Tuolumne data set. So there are times when that's, I would say it's probably more towards the post-peak time, but there are times that are flown before then too. So it's 53 flights from 2013 through 2019.
Oh, okay, thank you. I guess one thing I wanted to point out, because my understanding is a lot of those flights are later in the season, and you know, we would expect the station correlation to degrade during that time period, which I think is one of the benefits of ASO, is getting that late season view. But I do really appreciate your plots, especially showing, you know, the full range of uncertainty and the future precip and how that plays into it. I'm curious at some point, maybe now's not the time, but just to hear from Tom on how, you know, some of the skill that's presented, say, in Lindsay's model compared to some of the, like the video we saw this morning where there was a 2% error claim.
Yeah, so Pat Cormos asked a question about that. So that is based on the that's the minimum flow, and that's based on the Tuolumne work. And that again is based on the work that Chris Graham has done with the full range of data going back to 2013, including the 2020 data. And so that's where that particular number comes from, and no doubt the post-peak precipitation will have an impact on that April 1 forecast. The additional piece of this, though, is just that with ASO we can go and fly it immediately after the storms or soon thereafter, and give that quantitative update. So I think I'll put that reply out to, I think I had it in the answered questions, but that's where that number comes from, and that's the plot. And in fact, Wes showed it in his talk for those dates after which there's no appreciable precip. That's the uncertainty. The other thing is that in the Sierra, I think we're looking at about 5%, on average, about 5% of the flow, or 5% of the precipitation comes post-peak. And I think that number is more along the lines of 10% in the Colorado Rockies. So at any rate, that's that component of it. I know there's a question from Jeff Dozier.
One question from Jeff, and then we'll move to the next talk. Thanks, Gus. Jeff asks, any analysis based on statistics like a regression will do well most of the time, but it will also surely produce outliers some of the time. We see this in Tom Painter's slide earlier in the week about traditional forecast errors that sometimes exceed 100%. So the question is, what do the outliers of your analysis look like, and can you identify years when we don't want to trust the regression?
Yeah, so I certainly think 2017 jumps right out. And if Ethan wants to, he can jump in more because I know he's looked at this a little more closely than I have. So, you know, that is sort of a high year as an outlier. But I also think where we really saw things kind of start to break down, I'll say, although, you know, some applications in R squared of 0.8 would just make your day. But when you're trying to make these really, you know, highly precise decisions, that's perhaps not acceptable. And those were the low snow years or the low snow time of years. I think we saw that in the, you know, that number of flights needed, but that can kind of, you know, represent the predictability of, you know, that breakdown of low snow years for other times too. So, you know, the low snow years being fairly well represented in the 2013 to 2019 time span, you know, they only got up to a R squared of 0.8, even with 15 flights. So, I mean, any low snow year where your snow is dominated up high or maybe distributed differently, it's going to be tough.
Awesome. All right. Thank you so much, Lindsay. I'm running a little behind here. I'd like to try to catch up a little further, but thank you so much for that talk and excited to see how that project progresses. Our last talk in this session before lunch, Ty Brandt and Chris Castellano from the Center for Western Weather and Water Extremes at UC San Diego. Ty in his recent graduate work used ASO data to explore snowstorm accumulation patterns in Sierra basins. And Chris is bringing his weather forecasting and research background to bear on studying atmospheric rivers, forecast-informed reservoir operations, and associated forecasting tools. Welcome, gentlemen. Looking forward to your talk.
Hey, thanks, teams. So I'm going to share slides here. I'm hoping everybody can see my slides.
That's great.
Perfect. So I'm going to talk first and Chris is going to follow. And the title of our presentation today is Winter Precipitation in California, Sierra Nevada, Time to Embrace the Chaos. Become evident why we sort of picked that as we sort of move through this. I just want to mention that this work sort of falls out of work I was doing with Jeff Dozier in my PhD at UCSB. So that third chapter looked at sort of comparing WRF, or specifically West WRF, which is a flavor of WRF produced by the Center of Western Water or Center of Western Weather and Water Extremes at Scripps with ASO estimates of peak SWE. And we found that in certain years, West WRF seemed to perform better than others. And sort of the question that fell out of it was, well, why? What's going on in certain years that's not going on in others? And so I've taken this work to my postdoc at Scripps here and added some more co-authors, and we've been sort of digging into this as of late. And I want to mention that this work is still an active area of research. We welcome constructive feedback, but this is not published in any way, shape, or form, and we're sort of just moving further and further into the weeds as we go. Anyway, so mountain snow variability has led to huge investment, both public and private, over many, many years to basically improve forecasts of water runoff. I mean, that's kind of why we're here. I heard the last talk sort of about this. But one thing that I kind of want to emphasize is that forecasting needs, broadly speaking, can kind of be separated into two: water supply forecasting, so at the seasonal level, and then, of course, short-term forecasting. So that's more about hazard mitigation. And that's on the hours to sort of days basis. And, you know, the work that Scripps is engaging in is in both sort of camps. And the work that we're presenting here has implications for both these different sort of forecasting needs. Now, the forecasting science, and this is very broadly speaking here, has sort of been completed by two sort of different disciplines. You've got the meteorology and the surface hydrology. And from where we sit, and this is granted very broad brush kind of strokes here, but from where we sit, you know, sometimes the science has been sort of done by these two different sort of fields and sort of has remained somewhat separate or siloed. There are individuals that sit in the, the middle between these two fields and definitely produce papers and things like that, but that's definitely more rare. But the point is that these fields sometimes are siloed. They don't always have information that sort of permeates across the barrier. And that's what we're really trying to do with this work. We're trying to sit in the same room with meteorologists and surface hydrologists and bring everybody together and actually produce hopefully a paper at the end of this that uses both sides of the science. So the one thing that I really want to emphasize, because I made this mistake as a graduate student, is all the different pieces that can kind of come together that can influence the spatial distribution of precip. Now, this is really important. This diagram here on the left, which was produced by Ben Hatchett, a co-author of mine, does a great job of sort of trying to explain all these different pieces. But the point that I really want to drive home is just because you have precipitation in the mountains doesn't necessarily mean you have orographic enhancement. In fact, all these other different mechanisms that are kind of going on can produce very different spatial distribution of precipitation, but importantly, it's the phasing of these mechanisms, how they interact, when they interact, are they working, are they not working, that can drive the spatial and temporal variability. Now, the piece of this work that's kind of a little different than what's been done in the past is that, we can't really observe rainfall very well across, complex terrain. But what we can do is we can observe snow after the fact. And so this work is trying to use snow as sort of a proxy for precipitation. We recognize that there's a lot of other forces going on that shape the snow. But by and large, precipitation and the precipitation mechanisms that sort of deliver it are what sort of create the spatial distribution that we observe on a year-to-year basis. Now, as I said, the spatial distribution of SWE is principally shaped by these precipitation mechanisms. The rest in this list are not sort of, I didn't put them in a specific order because these definitely, so wind redistribution, sublimation, melt, topography, land cover, class, they differ in sort of their forcing or their ability to force the distribution of SWE depending on what scale you're talking about, what temporal scale, where you're talking about in a specific basin and things like that. But they're all things that we have to think about when we're talking about the distribution of SWE. Now, to reduce the uncertainty in the estimate of SWE over the many years, we've kind of come up with different ways of sort of estimating it or measuring it. We use snow courses, snow pillows, or snow observation sites that have snow depth sensors, for example, models and remote sensing, or possibly a combination of these. ASO Incorporated is a great example that uses all these different sort of ways at estimating SWE to come up with the spatial distribution of SWE. Now, as a snow hydrologist or as a card-carrying snow hydrologist, the first place I go when I'm sort of interested in looking at sort of SWE and looking at its variabilities, I go to the surface stations. And it's important to sort of mention that these are hard-fought, hard-won observations. And we have one of the densest gauge networks in the world in the Sierra Nevada. I mean, it's truly impressive when you look at the amount of data that we've collected over the many, many years that we have observations. And, when you look at the tuolumene itself, if you look up here in the top left, these blue triangles are basically where we have snow observation sites that could be associated with the tuolumene. And by and large, if you look at a transect of the tuolumene itself in orange here, or the elevational transect, you can see that above about 2,000 meters, which is roughly where the snow rain transition occurs, very roughly, you can see that we've got good elevational coverage of these snow pillow observation sites. Now that's assuming that they're behaving and that they're working in any particular year. But the point that I want to make is that when we start to look at how the SWE at peak SWE sort of points in the season compares to the elevational gradient, it gets really hard to basically understand sort of spatial context for these different years. We can see the magnitude changes. So 2017 in these sort of turquoise squares is definitely bigger than, for example, 2018 in these round filled in dots at the bottom. But understanding how the snow basically varies between sites is complicated. And part of the reason for that is that snow observation sites have to be sort of in low sloping terrain. They don't really have an aspect associated with because the slopes are fairly low. They're encapsulated by forests and things like that. And as a result of that, we need something to sort of give us more context. And that's what the Airborne Snow Observatory allows us to do. It allows us to look at snow in a way that we've never really been able to see it. And, you know, broadly speaking, when we look at these different years, there's a lot of interannual variability. And I really want to kind of zone in on two particular years because I think these are great sort of contrasting years that are important to sort of understand their differences. So, you know, water year 2019 and water year 2017. We both had, you know, both these water years had tremendous amounts of SWE, but the spatial patterns themselves are very, very different between these 2 years. You know, water year 2017 was much warmer than water year 2019. And you can see that reflected in sort of the low elevation amounts of SWE that we had in the basin in Tuolumne. But what's different about 2019 versus 2017 is this high amount of SWE in the very north part of the basin. And, you know, if we add subbasins, we generate more sort of spatial context and more understanding. So here's 2019 and here's 2017. In 2017, we had this very even distribution of accumulation basically occurring as, you know, measured by the SWE. In 2019, you can see this blanketing of the snow that really hit Cherry Eleanor and sort of the northern part of the Tuolumne, but didn't hit the southern part of the Tuolumne. And, you know, 2016 is a good comparison year too, because you can see Cherry Eleanor didn't get hit as much in this particular water year. We had more in the northern Tuolumne and less in the southern Tuolumne. So SWE can vary substantially between the subbasins. You know, looking at basins as a whole maybe isn't necessarily the right way to do that. But for a time saver, I'm just going to look at the Tuolumne right now and focus on that. So peak SWE, you know, I picked certain dates there that we were looking at previously for a number of reasons. But for the most part, what I was doing was picking the point where we had sort of the maximum amount of total snow within the basin. But how well does that estimate of peak SWE sort of fit with peak SWE from snow observation sites in the Tuolumne? And I've pulled out just a few snow observation sites and sort of plotted the progression of accumulation and ablation. And then over the top of it, I've got these black lines that represent the ASO flight dates. And then the red sort of vertical line that's in bold in red is the flight date that I picked for basically representing what I'm going to call peak SWE. Now, for the most part, ASO seemed to hit really, really nicely the transition from accumulation to ablation. That red line kind of sits squarely right at the point of peak SWE, especially at the higher elevation stations. Now, the point that I'm going to make right now is that peak SWE in and of itself is a bit of a moving target. It's not always, how do I put this? You know, snow elevation sites, and, you know, if we look at 2016 here as a good example, snow elevation sites differ in their estimate of peak SWE. Lower elevation sites transition from accumulation to ablation much, much sooner in the water year than higher elevation sites. And so peak SWE in and of itself is a bit of a moving target. You know, a good example, or another way to kind of think about this too, is that even within years, you know, you can have different water years that have sort of seasonal snowpacks versus ephemeral snowpacks. And this was work that was done or compiled by one of my colleagues, Ben Hatchett. So he was looking at using the Margulis data set as well as the Zhang et al. 2018 data set to look at ephemeral versus seasonal snowpacks in these different years. And what we were doing was sort of trying to look at, well, if we take a single ASO acquisition image and represent that as peak SWE, how does that differ, for example, than a pixel peak SWE? So if you maximize the amount of snow at any given pixel, how does that compare to ephemeral versus seasonal snowpacks? And what was interesting in 2015, if you look at the Margulis data set, is that the single ASO acquisition that I chose to represent peak SWE, the contour for that, or the snow transition line, is in green. And then the pixel peak SWE sort of transition is in red. And you can see that, lo and behold, using the single acquisition actually captured most of what we're calling the seasonal snowpack, which is what we're interested in when we're thinking about comparing this to precipitation accumulation and things like that. So in this particular case for 2015, I think I made the right call in picking that one particular image. So now let's talk about the SWE elevation relationship and how that changes between years. So these are scatter density plots. The blues represent basically more pixels. The whites represent less pixels. And again, what I want to really draw on is the comparison between water year 2019 right here and 2017 right here. So in 2017, we had this very steep SWE elevation relationship. We had a huge amount of outliers with absorbent amounts of SWE at the higher elevations in the basin. In 2019, we had this vastly different distribution. Even though we had similar amounts of total snow, the distribution of where that snow was located was shifted to lower elevations within the basin. We didn't see those extreme outliers. And this has sort of played out really nicely in the different sort of shapes of our, splines, which represent the sort of mean sort of snow per elevation across the basin. We can see these vastly different shapes. But, great care needs to be used when you're using these metrics, because if you just pick like the peak SWE from the spline and plot that, for example, against the total amount of snow, you'll see that it just looks like we've got a magnitude problem between these different years. But that's really not the case when you look at the shapes of these curves, as well as sort of the way the point clouds actually are shaped and how that varies year after year. And again, too, if we look at just how the point cloud is distributed across aspect, and I want to point out that I'm using aspects where the slope is greater than 10 degrees, you can see these sort of yin and yang profiles and how these kind of shift year after year. And the reason that we have these sort of blotches basically in the northwest and the southeast is because if you look at how the Tuolumne is set up as just sort of a basin, we have these ridge lines, particularly in the northern part of the Tuolumne, where you have northwest and southeast facing slopes. But again, if we just do a comparison between 2019 and 2017, you'll see in 2019, we had this very similar sort of distribution of SWE across many of the different aspects, whereas in 2017, a lot of our snow was sort of piled on the northwest facing slopes. Anyway, we're going to shift gears here and talk about the meteorology and talk about the interannual as well as sort of storms within years. I'm going to turn this over to Chris.
Okay, thanks, Ty. Full disclaimer, I'm a meteorologist, but I'm going to do my best to keep this section of the talk relevant for the target audience. And I'd like to kind of start out looking at the big picture, focusing on precipitation at the seasonal or even the annual time scale. And then I'd like to gradually work my way down to the daily or event time scale. So similar to what Ty showed in his analysis of SWE, precipitation in the Sierra Nevada exhibits substantial interannual variability. This is a time series showing the total cool season precipitation in the upper Tuolumne from water year 1982 through water year 2020. Here I've defined cool season as October through April. The gray bars represent the precipitation. The blue line represents the number of wet days, and the red line represents the number of dry days. Here I've defined wet day as any day with at least 0.25 millimeters or roughly 0.01 inches of watershed mean precipitation. And so in addition to the interannual variability, we see that total precipitation is strongly correlated with the number of wet or dry days, but some years are definitely outliers. For example, there were more wet days in water year 1985 than in water year 2017, but the total cool season precipitation was less than half of that in 2017. And when we dug a little deeper, we found that 2017 featured an unusually high number of landfalling atmospheric rivers that impacted Central California, whereas 1985 featured relatively few of these events. And so I want to emphasize that individual storm behavior really matters. Looking back at the time series again, we also notice a negative trend in the number of wet days in recent decades. And many climate models suggest that the precipitation regime in California will undergo pretty significant changes throughout the 21st century, with precipitation occurring less frequently, but the extreme events increasing in intensity. And these changes in precipitation frequency and intensity will present major challenges to water storage and flood risk management operations. Next slide. So besides the total precipitation, the temporal distribution of precipitation also within the cool season also varies considerably from year to year. So these plots are showing cumulative precipitation between October 1st and April 30th. for the 8 most recent water years. And for instance, if we look at water year 2013, the water year actually got off to a relatively wet start, but very little precipitation fell after the 31st of December. And so as a whole, this ended up being a rather dry water year. 2014 and 2015, as we all know, were both exceptionally dry water years. But you can see some notable differences between the two. In 2014, we got off to an extremely slow start, with more than 75% of the water year precipitation occurring after the 31st of January. 2015 was kind of characterized by these two very prolonged dry stretches with one major event in the middle. Water year 2017, as we all know, was exceptionally wet, but interestingly, the number of wet days in 2017 was quite similar to the number of wet days in 2016 and 2019. The major difference between these 3 years was the number of large or extreme precipitation events, which was much higher in 2017. So as these figures illustrate, the timing, the frequency, and the intensity of individual events really drives much of the year-to-year variability. And this has important implications for snowpack, water storage, and flood risk management. Next slide. And if we zoom in even further and take a look at some of these individual events, we see that there are really many meteorological factors at play. As Ty mentioned at the beginning of the talk, there are many mechanisms that influence precipitation and snowfall in the Sierra Nevada. And while the most extreme events tend to occur in environments with strong upslope moisture flux and orographic enhancement, these ingredients are not always necessary to produce intense precipitation. And to really emphasize this point, I'm showing two different cases, the 25th of October 2010 on the left and the 21st of March 2011 on the right. In the October 2010 case occurred in a very warm, moist environment with a strong landfalling atmospheric river that impacted Central California. And so upslope moist descent was likely very important in producing intense precipitation. By contrast, the March 2011 event occurred in a relatively cold, moisture-limited environment. And so there were likely other processes at play that produced intense precipitation. And I should also note that given the differences in the timing and the temperature during these two events, that likely produced a very different hydrologic response to the precipitation. So in the case of the October 2010 event, most, if not all, of the precipitation was falling in the form of rain, and that precipitation was likely either absorbed directly into the soil or led to runoff. Whereas in March 2011, a significant portion of the precipitation likely fell in the form of snow, and that helped grow the snowpack. Next slide. Another thing I would like to argue is that these different meteorological environments can lead to different spatial distributions in precipitation. And if we compare these two events, we see that the precipitation gradient by elevation was actually much larger in the October 2010 event than in the March 2011 event. Next slide. And in fact, when we look at all 95th percentile events in the upper Tuolumne, we see that there is considerable variability in the distribution of precipitation by elevation. So if I can drive the point home, meteorology is key to understanding the intensity and spatial distribution of precipitation and snowfall within the watershed. And individual events over the course of a season can really drive a large amount of the variability between different years. So I'd now like to turn it back over to Ty for some closing remarks.
Sorry, we just wanted to finish by thanking everybody for listening. As I said before at the start of the talk, this is still an active area of research, and We haven't presented a lot of the stuff that we've kind of looked at this point in time. But yeah, we'll open it up to any questions.
Awesome, thank you guys. That was a lot of range in there. Let's see. While we're waiting for, oh, there's Peter Voister's got a question. All right, I unlocked you, Peter. Go for it.
Unmute. Got it.
There you are.
Hold on a second. I got to turn off my phone. Okay. So can you hear me now?
Yep.
Okay. All right. So the question is, the next area of research, or maybe you're working on this, is taking all the ASO measurements and seeing how they could go into potentially be incorporated into PRISM maps, because what we find in PRISM maps that rely on, you know, the precip stations in the mountain areas that, you know, they notoriously undermeasure the actual precip. If you just compare the precip to the SWE, you know, you can see that, at least in the Mono Basin. So is there an area of your research that's going to evolve, or could it go to the place of comparing PRISM precip maps with the what you get from ASO, extrapolating the SWE measurements and additional precip to construct a more accurate map of precip over the Sierra?
Chris, do you want to take that one?
I don't know. I mean, I think that's a great suggestion, and you're definitely right about the issue with PRISM, and that it tends to underestimate the precipitation at higher elevations, particularly during these very extreme events, likely due to, I don't know if that was something that we were planning on doing, but I think it's definitely worth considering.
Oh, well, I want to encourage you only because I've been waiting for, this is what you presented today, just found, oh, if anybody could do it, it's the direction your research is going. So, you know, but maybe there's other people who are already doing it. It's just, that's one of, you know, the PRISM is very useful in some areas, but in mountainous areas, it's just not as useful as it could be. But now with the ASO data, we can correct. Or we can.
Yeah, Peter, we have looked at that a little bit, and there's Pat Cormos has added a comment as well. He says we're seeing less precip than PRISM suggests in the CBRFC, the Colorado Basin, based on just a few flights. Another reason these flights are so important. Yeah, one thing that PRISM can't really capture, because there's no stations above tree line, is commonly there's a drop off in accumulated SWE at upper elevations, and some of Ty's work showed this as well. And there's a number of potential factors contributing to that. You know, moisture starvation due to the orographic mechanisms. There's of course scour and wind transport and sublimation in that windy environment up high, et cetera, et cetera. But the key thing is that there's no really consistent enough, at least that we've been able to detect so far, pattern in how that works that you could just imprint on, say, a PRISM normal or something. You can't just say, oh, well, the PRISM lapse rates are incorrect, let's use this lapse rate instead. It varies so much with all the different storm dynamics, as Kristoffer and Ty have showed so well here, that it's difficult to make those sort of blanket assumptions that have to go into a more generalized model like that.
I understand that, and I was getting I didn't mean to get too excited, but I just see that there's some use for the ASO data in that kind of perhaps of looking, is it useful for updating, refining PRISM maps, and as you said, all the issues that need to be taken into account. But I just thought that was something where another use application of ASO data that that perhaps someone like the group somewhere is looking at that.
Yeah, for sure. Thank you, Peter.
Yeah, thanks for the suggestion. we'll definitely be taking a look at it. I think I just want to echo Jeff Deems there just really briefly in that PRISM does have some assumptions kind of baked into it that make it, you know, more challenging for when we've got storms that are not behaving in a way that's sort of classic, where you see, you know, typical sort of orographic enhancement. So if you've got a very dynamically forced storm, that's where PRISM really tends to struggle. It's interesting from, and maybe I'm speaking out of turn here, but when I'm working with meteorologists, you know, they use PRISM in a way to sort of figure out, okay, where do we want to take a deeper dive into? And then how do we apply then more of these mesoscale models that have more sort of meteorology baked into them that really sort of pull events apart? And it was just an observation that I've had about the way they tend to work and do things. I think that's reasonable to say, Chris, isn't it?
I guess so. This is a fair criticism.
One thing that popped out to me, I wonder, Chris, if you could scroll back, or Ty, if you could scroll back to the time series graph where you're showing number of wet days and number of dry days and number of AR events. That's the one.
Mm-hmm.
You know, this one really popped out to me, and I think it illustrated even more of your points than you articulated while you were speaking about this slide. But just that, and I think it was Kristoffer said the word equifinality earlier in his talk, that you can end up with the same amount of SWE on the snow pillows and have a vastly different time series getting there and vastly different spatial distribution of events that produce that. And the contrast between, you know, that like 1983 and 2017 couldn't be more stark. I mean, it's just almost identical in terms of total precip on the measurement stations, but the event counts really show that they're completely different years. And I wonder if there's, I mean, you guys are obviously dissecting a lot of the meteorology and the synoptics processes here, but I wonder if if you could comment on, you know, how the high resolution data that ASO is providing can help us deal with that.
Sure. Yeah, I think that's on my end. You know, from my, I mean, I think Deems, you mentioned at the start, there's kind of two ways to use ASO data to kind of go after meteorology. There's flying the individual events themselves, and that produces sort of, in my mind, the best result for directly comparison to, or directly sort of comparing to models like WRF. How much did WRF produce via precipitation? How much did we actually measure? And where was that precipitation sort of distributed? And the other way to do this is to, you know, use ASO during the accumulation period to sort of keep track of what's going on and how things are changing as a result of these individual storms. And the way I have lately started to think about this is that the earlier you guys fly, and the more time we spend sort of trying to understand these individual extreme events and storms and how they're compounding on each other, the more sort of we're going to be able to sort of manage the more extreme events as they come, you know, in the future. And so this is kind of like insurance, if you think about it. But the high resolution data gives us unprecedented views of slopes and aspects that we just can't get with station data at this point in time. Station data is still critical because it allows us to sort of understand these individual events temporally. But the spatial context that ASO provides is unprecedented. And, you know, you can use reanalyses and things like that, but they're not a measurement. ASO gives us the measurement, the spatial context. And so that's why it's so unique as a data set. And that's why we're leveraging it in addition to all these other meteorology-based sort of products and to kind of do our analysis.
Awesome. Well, there's so much that you guys have presented here, and I want to give you a shout out for the wide array of work you've done and continue to do.
Thank you.
And in that spirit, I'd like to, you know, congratulate all our presenters in this session. There's a whole lot of good stuff going on, and I feel like we could spend another week going through all of these different research applications alone, not to mention all of the operational stuff. So Thank you guys again. Thanks again to all the presenters in this session. We are only 45 minutes behind schedule. Lunchtime now. What do we think? A 45-minute lunch? Anybody discussing this yet?
Yeah, let's do that.
So resume at 1:30 Pacific time, 2:30 Mountain for those who are math challenged like I am. And don't forget, Tom will be running through the results of the poll and announcing the winner of the Rich Marino ASO t-shirt. And then we'll jump into our last session.
And in the final discussion, I'm also going to put up a couple of slides just to speak to what I was trying to answer Gus on, but there was a hammer drill on the other side of the wall and I could not think straight at all. But I've got a couple of slides to put up there just to speak to what that number's about. So hopefully you can all make it back, in particular Gus and Pat, who've asked that question this morning. All right. So 1:30.
Awesome.
Thanks all. And I want to first thank Liz for going through all the answers and figuring out, well, first of all, putting together the wrong answers and to supplement the questionnaire, and then likewise for going through and adding up all the successful scores on the and the fails.
Yay, Liz!
Arriving at the winners, yeah. Okay, so question number one, how many years after the formation of the California Cooperative Snow Surveys Program did ASO Inc. form? Yeah, it was 90 years. And I think back to Dr. Church's first snow surveys, it was more like 110 years. And it's too bad he's not here today to be able to see what the actual spatial distribution is. Who was the first DWR employee to fly on ASO? I like that everybody got that right. Shows they were paying attention or that they can read, given that there were no other viable answers, but it's cool that we had an astronaut thrown in there as an answer. How many times has ASO flown the Tuolumne River Basin? And we couldn't really keep track, but we think it's more along the lines, it's like 58 times now, something along those lines. And we're looking forward to when it's been 1,396.
That one was easy because it had to be the approximate answer.
Right. What's the deepest snow in California that ASO measured in water year 2017? Yeah, that was 29 meters over in the Minarets out here to the west in the San Joaquin. And what NASA planetary mission was on the news when ASO first flew its Tuolumne snow-free data? The MSL is right, and at that time we didn't have digital 395 in here, and so we had slow internet. We couldn't tap into JPL to watch that, so we had to watch it on CNN on the lousy TV at the Shiloh Inn. So the Tuesday poll results. All right, what was the first non-government entity to pay for ASO data in California? That's right, the Friant Water District, Friant Water Authority, and Jeff Payne was the person who was really pushing that along. He has since moved on to the Bureau of Reclamation. What is the first country outside of the US that ASO has processed data? Switzerland. We're looking forward to Canada, Chile, and New Zealand, but we're not quite there yet. What was the first national park ASO flew snow on outside of California? And that was the Olympic National Park, not Rocky Mountain National Park, which was the Rocky Mountains, the national park that I grew up looking at as a boy. Question 4, what was the first national park ASO flew outside of California? So on that transit from Colorado to California for our snow-free work, we flew over the Grand Canyon and didn't fly the whole thing though, but just some transects through there. What NASA program was originally formed around the ASO mission? That was the Western Water Applications Office. It was originally called the Center for Snow, Water, and Availability. And we could never figure out how that got put together, but that was based on conversations that I had had with the Applied Sciences program at NASA about what was required to really scale this around the Western US. So many of the conversations we're having right now are those that we would have been having if the program had remained at its core intention.
I'm disturbed at the other choice percentages there.
Well, oh well. Oh, which of the following was not the name of an ASO server? It was not Everest. We would have called it Chomolungma or Sagarmatha, if only because we like to have machine names that have that require lots and lots of typing. Okay, and then yesterday's poll results. When was the first ASO snow on flight in the Colorado River Basin? That's right, April 2013. I think it was April 15th in the Uncompahgre. What year was the first ASO snow on flight in the Rio Grande Basin? 2015. And as a few people mentioned yesterday, Joe Busto, who was with the Colorado Water Conservation Board, spearheaded that, got us going, and he just was an incredible champion. I think many of you met him at the ASO workshops and at AGU, and we lost him to cancer earlier this year. Who is the strategic GIS partner of ASO Inc? Yeah, Esri, you've seen that. Who's the clothing partner of ASO Inc? Ridge Merino, wherever there's the logo. What is the official gin of the ASO program? And this is the one that I think people had the most wrong. It's jackalope out of Western Colorado, even though aviation would be a pretty awesome choice. So the winner is Ethan Gutmann and Ryan Currier. And so there was some question as to whether we should have a tiebreaker, but we decided instead to get you each a shirt. So send me an email, or Liz, anybody on the team, an email with your size. I'm going to guess both of you're either mediums or larges, and we will get that embroidered and sent out to you. All right, let me stop there. I'll hand it back over to, am I handing it over to Jeff? Oh no, I'm the session chair. Never mind.
It's all you.
All right, so let me stop sharing and not hit delete on the Zoom. And Kat, you're up next, right?
It's actually Jenny.
Yeah, it's Jenny.
Oh, you're doing
Jenny's video first, yeah. And she is
I have the video.
Okay, why don't I, Liz, since you and Jenny have been communicating, let me hand it over to you.
Well, Christina's gonna play the video, and then Jenny is online to take questions afterwards.
Okay, great. All right, I will stop talking and hand it over to you to Christina.
Yes.
Liz, are you able to play the video? Because Zoom told me I would have to install something in order to be able to share the audio and then restart Zoom, which is not a good option.
Oh,
So,
yeah, let me grab it up real quick.
not prepared for that. But if you want me to, I can do that.
No, that's okay.
Okay, cool.
Let me just grab it here. Can you unshare then so that I can?
Oh,
or
I forgot I still was. Yes.
I can meanly steal it from you. All right, let me close the questions so that's not in the way. Okay.
Hey y'all, my name is Jenny Fromm. I'm the lead water manager for the Sacramento District of the Army Corps of Engineers. I'm very excited to be here today. It's the 5th ASO workshop. I've been to all 5, and so Tom finally talked me into presenting. So today we're going to talk about flood control operations. So on the agenda, we have the Corps' authority, Sacramento District and what we do, flood control operations, the use of forecast and reservoir operations, and the Corps water management system. So where does the Corps get their authority for flood control management? It comes from Section 7 of the Flood Control Act of 1944, where it states that the Corps will prescribe the rules and regulations in the interest of flood control. The project owner is responsible for real-time implementation of the water control plan, but the Corps has the authority to determine the flood releases in the flood control space with input from the owner. So here's a map of the Sacramento District projects. As you can see, we span 8 states, and we have flood control projects in 3 of those. Most of them are in California, but we do have 15 in Utah and Colorado. Additionally, you'll see 3 projects that are outside of the district boundaries. Those are in San Francisco District. And historically, Sacramento District has done the water control operations for San Francisco District. However, a couple of years ago, we handed off the reins back to them in San Francisco. However, in Sacramento, we still do their data management. So here's a breakdown of those projects. We have 3 debris dams, which is, there's no flood control operations. An example would be like North Fork Dam, that you'll see over here on the right. We have 19 Corps projects that are owned and operated by the Corps with flood control. 17 of those are in Sacramento District, 2 are in San Francisco. We have 32 Section 7 projects, which is what we call the projects that are owned and operated by others based on the Section 7 of the Flood Control Act of 1944. They're owned and operated by others, and they have a flood control space. So within the water management section of the Sacramento District, we have 2 sides of the house. We have the reservoir operator side of the house, which I am the team lead for. We oversee flood control operations. We set up the rules for flood control with essentially what we call a water control manual. We aid in reoperation studies. We train dam operators. So every year we go to our Corps projects and we walk through the water control plan with the project staff. So that way, if we were ever in a situation where communication is lost between the project and the water management section, the project staff know how to read the water control plan, they know how to implement it, and they're empowered to do so. We also offer this up to our Section 7 cooperators, and some of them take us up on it, but if you're interested in having us come and talk to your project staff or any of your staff about the water control plan, just let us know and we'll come on down. We also assist with planning studies, we assist with dam safety studies, and we also prepare deviation packages. And a deviation package is a formal approval to deviate from the water control plan. The other side of the house is what we call the water control data system. So essentially they're in charge of the data. So they do data entry and data QC. They operate and maintain the over 100 gauges that we have within California. As you can see a map here on where those are located. They also help train dam operators. They do PC refresh and security at the projects themselves, including cybersecurity. And additionally, they'll do other projects like cameras, water quality issues. They'll help with dam safety and instrumentation and general maintenance. So let's talk about the water control plan itself. So the water control plan is found within the water control manual, or sometimes it's called a reservoir regulation manual. In Appendix A, there's a standing operator instructions. There's also the water control diagram, which is essentially an 11 by 17 of the water control plan. And then if a project has a gated spillway, they have an additional document called an emergency release spillway diagram. So the water control manual is the guiding document that specifies how the Corps operates the reservoir within the flood control space. It provides operational instructions to personnel involved in managing the reservoir, including emergency situations, but is not your emergency action plan. That's a separate document. It prevents loss of institutional knowledge and ensures unbiased operations and that the mission priorities are transparent to the public. So before we get into a water control diagram, let's just talk about general operating zones within a reservoir. You're going to have your dam itself, your top of dam, your spillway crest, your surcharge pool, which is essentially a dam safety space. You're going to have a flood control pool and your water conservation pool and your outlet. And then how that relates to your water control diagram and your emergency spillway release diagram, if your project has one, is like this. So you're going to see a drawdown in the fall where you're drawing down the storage of the reservoir so that way you have the maximum amount of flood space in the winter, and then you're going to have a spring refill so that way the project can refill in the spring and summer. And then if you have a gated spillway, that additional diagram called the emergency spillway release diagram is here. It tells you how to operate the gate in an emergency. So typically, this is what a water control diagram looks like. So as you can see, you're going to have gates at the bottom. You're going to have on one side of the y-axis storage, which is what you'll see here. And then also on the other, you're going to have flood control space. So, and then within the diagram itself, you have the conservation space. This is where the water users or the project owner has control of the operation. And those may or may not be the same entity. In the West, all the Corps projects, the Corps does not own the water for those projects. It's the water user. And in the East, it's different. And then we have the rain flood space up here. Rain flood space up here, which is what we talked about before with the drawdown period in the fall. The max amount of flood control space in the winter and the spring refill. And then we also have the conditional space here, which is where we're looking at the snow forecast. So typically in California, that'll start in February, but in other projects in Utah and Colorado, it'll vary between January and March. So what's on your water control diagram? So it's going to have the top of conservation calculation, which is that calculation gets done every single day, and it will tell you the amount of flood space that the project needs at any given time on that day. So things that could go into that calculation are basin wetness. So if the basin is wet, you're going to need more flood control space because when it rains, the water is going to run off into the reservoir very quickly. If your basin is dry, you're going to need less flood control space because when it rains, the soil will absorb a lot of that water and it won't run into the reservoir. For projects that have upstream reservoirs, they could get credit for the space in those upstream reservoirs, the snow calculation. And then also in the San Joaquin, most of the projects will take into account irrigation demand in the springtime. So in the San Joaquin, starting in February, when we're looking at the snowmelt space, we're looking at what's the forecast for the snowpack, what's the irrigation demand based on the forecast of the snowpack, and how much flood space, how much space do you already have in the reservoir. and that calculation will determine how much flood space you actually need. Additionally, on the water control diagram, we're going to have the downstream control location and release limits. Any rate of change for flood control releases increasing and decreasing, because sometimes they're different, and any other rules notes specific to that project. So let's go look at an example. So here's Don Pedro's water control diagram. You can see the dates at the bottom. We got storage over here and flood control space over here. We have the conservation space in green, the flood space in blue, and the conditional space, snow space in pink. So once February 1st hits, we're looking at the Bulletin 120, saying what the forecast is for that particular day. We are looking at, we're talking to the project owner, so we're talking to TID, saying, hey, what's your demand? And then the calculation's also looking at the amount of space that's already available in the project itself in order to do the calculation. So if we look back at 2017, here's a plot from the Corps' public website. So let's walk through the plot itself, and then we'll talk about what we see here. We got precip at the top. Here in this section, we have the storage of the actual reservoir. We got gross pool on this line. The gray space is the conservation space. The white space between the gray space and gross pool is the flood control space. And then the blue line represents the actual storage of the project itself. So you'll see starting in February how the top of conservation, is moving around every single day, because it's taking into account the forecast from the Bulletin 120, the irrigation demand, and then how much space is already there. And then at the bottom, we're also seeing the inflow and the outflow on this section. So if we look at what's a typical project in Utah and Colorado, they look a little different. Some of them in Utah have a rain flood space, so it'll be similar to what we just looked at. But then some of them, a lot of them in Utah and Colorado do not have a rain flood space. So you're going to only have a conservation space and a snowmelt space. And in Utah and Colorado, for these projects, irrigation demand does not come into the equation when it comes to calculating the top of conservation. And in Utah and Colorado, we use the Colorado Basin River Forecast Center forecast for these calculations. So here's an example of Red Fleet Dam and Reservoir, which is in Utah. Again, it's the same format and how it's laid out. And then starting in February, you'll see how the top of conservation changed. There were a couple of flood control releases that we had to do during that time frame in 2017. But it just shows the importance of having good long-term forecasts because it really does affect the amount of flood space you need for a reservoir. It affects, what operations we might do within that. So I'm excited that the ASO folks are working with the Bulletin 120 folks and also starting to work with the RFCs, because that means that it's going to tackle both the long-term and the short-term forecasts that we are using daily. So here's just some pictures of some of the data we use from the RFC for the short-term forecast. We're looking at the ensembles. We're looking at what the weather forecast is. How much precipitation do we expect is going to be happening in the next couple of days. We're looking at what's happening downstream. So we talked about long-term forecasts regarding snowmelt data and snowpack, and that's where ASO comes into effect. But then we're also looking at the short-term data from the RFCs. So I'm hopeful that when it gets to, the snowmelt season, that ASO and the RFCs continue to work together to provide us the best available data possible. So next steps from a Corps perspective is what we call the Corps Water Management System. So this is a suite of models that the goal is to have a real-time, fully integrated hydrologic and hydraulic model. So the Corps wants every district that has a water management mission to have these specific models, so that way there's consistent operational tools across all the districts with a water management mission. And in SAC District, we've started working on these models, and I'll talk about that in a sec, but I want to talk about first, like, what goes into these models. So there's the meteorological processor, MSP. There's a hydraulic model, which is HMS, a reservoir model, that's ResZoom, a hydraulic model, which is RAS, and a flood impact analysis, which is FIA. So it's looking at what kind of damage is this particular flood could occur. So if you're familiar with HEC real-time simulator, RTS, essentially RTS is the public version of SWIMS. SWIMS is based on an Oracle database, which is also where we house our data. And then RTS is Windows-based version of SWIMS without the Oracle database. So this is the kind of the next steps that the Corps is looking at to do real-time operations. So in SAC District, we have a lot of these models built already, but none of them are ready for real-time operation. We have the Truckee model built, we have the Tulare model built, we have the San Joaquin model built, the Sacramento model built. The Upper Colorado is in between 50% and 75% built. And then the Great Basin, which is in Utah, just got kicked off, so it's not quite at 25% yet. Like I said, none of these are fully operational. They still need to be calibrated and validated. So my hope is for water year 21 is that we start moving these projects towards use of full-time operations. So we'll start with looking at the Truckee, the Tulare, the San Joaquin, and the Sacramento, and then we'll move on to the Upper Colorado and Great Basin when those get completely built. So that's all I have for the day. We talked about the Corps' authority, SAC District, and what we do, flood control operations, use of forecast and reservoir operations, and the Corps water management system. So thanks for having me. Let me know if you have any questions, and I hope you have a good.
Thank you, Jenny, electronically, and thank you, Jenny, who's here.
Hi, thanks so much. Yeah, with the Corps' limited ability to be participants in Zoom calls, that was the best I could do. I wasn't sure if I could share my screen or not, but at least we can join you, because a couple of months ago we couldn't even have joined you on a Zoom call. So
right.
Thanks for having me.
So while we're waiting for questions to get in there, I have a quick question. It seems based on your description. First of all, thank you for finally being a speaker at the meeting, but also attending all the meetings. It seems that some of the early season flights and that quantification can still be quite useful for getting going on the season for you. So for instance, January 2017, when we had enormous snowfall here in the Sierra Nevada, would have been useful in getting a head start. So I'm just wondering your thoughts on cadence of acquisitions in the accumulation season versus the snowmelt season.
You're right. Like having that first forecast in February in California is super important, because it's what we look at to do how much flood control space we need starting February 1st, but it's also what the project owner and water users are looking at for their irrigation demands. So, yes, there's many other tools in our toolbox to figure out like what the irrigation demand is going to be. I say that like I don't know what the irrigation demand is, but others have tools in their toolboxes. So, but like since we use the Bulletin 120 50% for our flood control calculation, like having that be accurate at the beginning of the season is just as important as later in the season.
Okay. All right. Great. All right. So Jeff, let's see. Jeff Dozier is saying the Bulletin 120 forecasts include estimated values, but they also include the 80% exceedance probabilities at 10% and 90%. how do you use the uncertainty band in the decision about releases?
Well, we definitely talk to the water users and the project owners. Like, we're not in a bubble here. From a calculation perspective, though, even though we're not legally bound to use anything, historically, we've used the 50% bulletin 120, and we've just continued to do that. If there was a reason for us to switch to use the 90% or the 10%, depending on the circumstances, we have the flexibility to do that. It's just at this time, we haven't really had those conversations with the project owners and the water users. I'm open to have those conversations. And since we are not legally bound in California, Utah, or in Colorado on what we use for forecasts, that means there's flexibility to do so.
Right. It would be interesting to have a conversation with you and with Steve Haugen and Matt Meadows on 2019 and their decision to get out in front. So our numbers had pushed past the 10% exceedance, and that motivated them early to start working with their customers and keeping water active for irrigation instead of waiting to potentially run it in a flood call. So it'd be great to talk with you at some point soon. I'm gonna set that meeting up.
Okay. Sounds good to me.
Right. Let's see. No other questions and no hand raised that I see. All right, Jenny, thank you so much, and thanks for coming on live as well. It was great to see you.
Oh, no problem. Anytime. And like, if in the future anybody has any questions, like, feel free to reach out to me.
That sounds great. All right. Have a
Thank
good
you.
week. Thanks. All right. So I was checking with the team, and I think I know that the switch was just Jenny and Kat. And so next up is Micah Sandusky from M3 Works, which is the new-ish company that is going to be doing modeling for the integrated SWE product. Mike,
Hey,
are
Tom.
you there?
Yeah, I'm here. Can you hear me?
Yes.
Cool. All right, let me just share my screen.
See the slides.
All right, how are we looking?
Looks great.
Cool.
And a nice shot there. I like it.
Thanks. Hi, everybody. For those of you who don't know me, my name is Micah Sandusky, and I am here to talk about ASO and M3 Works and modeling for an integrated SWE product. I want to apologize in advance if you hear my dog barking. The mailman decided to come right now, and he is my dog's mortal enemy. So let's dive in. So M3 Works, for a little background on who we are hydrology-focused modelers and software developers from the core team that created the automated water supply model. The automated water supply model is the operational framework that wraps the ice snowball snowmelt model. Basically, we're here to run awesome operationally, and that means focusing on operational needs and delivering the modeling products that can help with water supply management and forecasting. Also, we have a decent amount of experience writing code for data pipelines and for physical models. So anything that we can really write code to help out with at ASO, we are here for that as well. The team is Micah Johnson, who is a software developer with a background in snow modeling, as well as experience building and designing snow instrumentation. And then myself, gonna sound familiar, but another Micah who is a software developer. And I also have a background in snow modeling, as well as wind modeling for wind power in mountainous terrain. What I'm really excited to talk about, though, and here to talk about, is our partnership with ASO and what that means. So we're here to support ASO in their mission for accurate SWE measurements and runoff forecasts. And that means integrating those ASO remote sensing products into the model and providing that density component for the ASO SWE. Essentially, we're bringing ice snowball modeling in-house to ASO. I've thrown out modeling a few times already. So what do I mean when I say modeling? Basically, we are running the physically based distributed snowmelt model ice snowball wrapped in that modeling framework of ASOM, which handles the day-to-day operational running of the model. That includes distributing of the forcing variables from the NOAA weather model called the High Resolution Rapid Refresh model, and then managing all of the data and actually running iSnowball to get the SWE and other variables and density out of the model. For a little background on ASOM, it was developed at ARS, so shout out to the ARS crew who I think is attending today. It was created to streamline the operational modeling efforts that were pretty manual and ad hoc prior to the writing of ASOM. It avoids that manual script running that had to be done to distribute the variables and to actually run iSnowball. And it also serves to organize the inputs and outputs. Additionally, it tracks and documents user inputs. It allows for integration of ASO snow depths into iSnowball, and it allows for strategic tuning of the inputs and model parameters so that the modeler expertise can make its way into those results. This year, we're focusing on a few key ASO product integrations. So of course, as Kat showed earlier, we can integrate those snow depths, and that has a really positive effect on the snow distribution within the model. And then this year, we'll also be using the ASO DEMs. So here you can see an image of Senator Beck and the DEM for that. On the left, we have what ASOM and iSnowball have traditionally used, which is the 10-meter USGS product. And then that's upsampled to a 50 or 100-meter cell, depending on which domain we're talking about. And then on the right, we have those that half-meter product from ASO. So we're starting from a really high resolution product before we get to the DEM that will be used for the model. We also are looking at using the ASO veg data in the model this year. And then moving forward, we're really interested in exploring integration of more of the remote sensing layers. So there's a lot of great data that ASO produces, and we think that it can really help out with improving the modeling results. And there goes my dog. Another thing I'm really excited to talk about today is snow modeling in the cloud. So this year we will be running ASOM and iSnowball in Amazon Web Services, and we've already written some tooling to get it up there and have seen some success so far. And this means we're no longer limited by compute resources. We don't need to own and maintain our own supercomputer. We can spin up the resources that we need in Amazon Web Services. The effect of this is that we can scale to a larger number of basins and larger basins simultaneously. And that's a really big deal. This year, like I said, we've written some tooling to get ASOM up into the cloud. And then moving forward, we are interested in re-architecting key parts of ASOM to really take advantage of those advancements that cloud providers like AWS have made available. With that, we actually have our first results from the cloud. So some of that tooling that we've written really focuses on decreased time to results. So going from I want to model this basin to having the DEM, the delineation, and then full model runs. And we have our first couple results from that. And we just decided to play around with expanding to some new basins to make sure that we can. So on the right here, we see the Payette River Basin in Idaho. We ran a good portion of water year 2020 for the Payette River Basin to see the results there. And we can see the snow cover figure created from those results. And then just this week, we decided to spin up and run Senator Beck for 2020. And so we ran through August 13th in Senator Beck, and then using a software called SWE, which was also developed at ARS and based on the SLF streamflow model, we modeled the streamflow for Senator Beck as well. So here you can see the pink line is the modeled flow coming out of SWE, and then that dark blue is the observed flow with that gray border. And then on the top there, you can see the SWE, which is surface water input, which is another output product from iSnowball. Lastly, I just wanted to touch on our future plans and where our priorities are. So again, that shared goal for accurate SWE measurements and forecasts is really our #1 priority. We think this is just a really exciting program, and we're really excited to be a part of it. Secondly, stability and scalability of the modeling system is a big deal to us. We want to be able to expand to larger basins, to new basins, and really continue to provide the results when everyone needs them. We're also interested in improving the modeling framework. So based on stakeholder feedback, based on your feedback. If there's a question you have or something that you think the model could benefit from, we're interested in hearing about that because it's something we might be able to implement. Fourth, and Kat touched on this earlier, it's really important to be able to turn around the depths, integrate them into the model, and get the results back to ASO quickly. So we're looking at a full automation of the input of those depth measurements. So if ASO has the depths at 2 o'clock on a Saturday morning, it should be as easy as them uploading the depths. And we want to integrate that into the model automatically and turn the results around as soon as they're available. We also are interested in improving the model density, as that's a key component of the ASO SWE. So anything we can do to look at including measurements and observations to improve that density field as much as possible, we are interested in that. And then lastly, as we showed on that last slide, we're interested in streamflow integration and forecasting, because that's a big deal. And we think there's a lot of promise there. So we will continue to look at that as well. So with that, I want to say thanks to Tom and ASO for having us here. If you're interested in learning more about us, you can find us at m3works.io. There's a lot of contact info there. And I'm happy to answer questions. We also, I think, have Micah Johnson on to answer questions as well.
Micah, that was great. I see Peter Vorster has his hand raised, and I think there's more hands, and then Jeff Dozier has a question. I want to jump in ahead of everybody though, and just point out that that along with ASO Inc, which is the technology transfer out of NASA, what you're seeing with M3Works is a technology transfer out of ARS, and the research machine that that is sponsored by our federal government as well as state governments in these particular cases is working exactly the way that it's supposed to. The teams have worked really hard through the years together, and not at the very beginning with any intention of necessarily moving this out into businesses, but as we moved along and had the successes that we've had, and obviously there's so much more for us yet to do. Still, the potential was realized there to do that technology transfer and now be able to expand to across the Western US and likewise to have that influence worldwide. So this is a way in which that federal investment through these federally funded research and development centers is playing out for the good of the nation. Let's see, I'm not sure who went first. Who else has a raised hand? There's one raised hand or two? There's one. All right, well, I'm gonna go with older first and let Jeff Dozier ask his question. If I can find everybody. Jeff, I'm gonna let you speak to it instead of reading it myself. Take it away.
Okay, yeah, well, I printed it out, so Micah can also read it. But the basic issue is that I think we've got pretty good evidence from some of the presentations we've had that the measurements, the ASO measurements of depth have pretty low uncertainty. And, you know, it's kind of on the centimeters magnitude. So therefore, the uncertainty in the SWE really depends on the uncertainty in the bulk snow density. And, you know, over lunch, I reread some of Danny's papers since I was Danny's advisor. And there's a table about how iSnowball estimates the density of the new snow, but I couldn't find the details of how the evolution of bulk density is modeled. And so the convoluted question that all of this raises is, what are the likely values of the bias and the RMS error of the bulk snow density through the season? And how do these propagate into the error distribution of the SWE estimates? And how should we go about validating what we've got?
Micah, while you go towards answering, I'm going to commandeer the screen sharing and show you the paper that we're all on is still being worked on, and Danny went into retirement, but we're dragging him out of retirement to complete that paper. But Micah, go ahead.
Yeah, and Micah Johnson, if you want to jump in on this as well, you've done a decent amount of work with the density. I guess that first piece of the density of the new snow, there's definitely been some work done on that more recently when it comes to including the amount of new snow that's falling to basically bias that toward, originally it was a little bit too light and fluffy basically in the model. And so there was some work done to include some factor for how much new snow fell. But in terms of capturing the uncertainty, there definitely needs to be some more work done into that or looked into that. But yeah, I mean, we're doing the best that we can with the model, and I think it shows some pretty good results. I don't have numbers to put to it right now, though. Maybe Micah Johnson wants to speak more to that.
Yeah, I also don't have those numbers, but part of the issue is that some of those initial validation pieces that were done on iSnowball weren't done using the inputs we're using now. So there hasn't been a paper that's evaluated iSnowball with the inputs that we're using currently. And I think that's the next piece that needs to be done, is basically a performance study on the new modeling system.
And Kat's going to be speaking to some of that. Kat's over there, socially distant. But that paper with that paper that Danny's leading, that was an update to the bulk density modeling after the 2017 season, when we saw the huge accumulation in the Sierra and some of the issues with the bulk density modeling. And so we've gone back and done updates to the previous data sets based on that modeling. But there's an additional piece to this that comes in the assimilation of the in situ measurements, either the snow courses, the snow pillows, or the field measurements that we make regularly as we can. And we're hoping, as I mentioned before, with the program that Liz and I are working on with students, towards getting more and more density measurements out there. But at any rate, Kat will be speaking to that. But I will say that the whole reason that we started working with iSnowball and have continued working with iSnowball was based on the dust and snow work we were doing in the Colorado Rockies, and the snowpack modeling we were doing in the Senator Beck Basin and at the Grand Mesa study plot. And what we had found was that, at least in terms of the Rockies snowpack, until the last about that much snowpack, iSnowball or Snowball in that point case did really, really well with the density modeling. Now, we didn't have accumulations like we've seen in 2017 and 2019 in the Sierra that created that need for an update to the model. But at any rate, in general, the model does very well, and the further assimilation of those in situ measurements is a really important step in this. And Kat goes to that extra step once the distributed fields come in, and making sure that those are as well constrained as possible. Peter, you are now allowed to talk.
Okay, can you guys hear me?
Yeah.
Yes.
Okay, and I'm honored to have been have Jeff Dozier being that he's older, and I consider him the first hydrogeographer, and all the rest.
It was age over beauty.
Yes, age over beauty, but it looks like if you have a watershed that needs forecasting short term as well as seasonal, but short term, and it doesn't have any in situ measurements from snow pillows or courses, but you have a gauge, this would work well, right? I mean, if you need the forecast, it's based upon the ASO and then the nice snowball. It sounds like this would be a great tool to have, even without those, for lack of a better word, calibrating measurements. So that was question one. And question two, right on for your acronym, because I assume all those high school and college students that are going to be recruited to get more density measurements to feed into the model, they can then say, my data is going into an awesome model. Was that intentional or?
Yes. To get the high school kids involved.
All right, good for you. But yeah, so the first question was about, you have a stream flow gauge, but no in situ measurements. But if you have the need for the short-term forecasting and seasonal forecasting, and Mill Creek is the example I gave on Monday, this looks like would be a good package to put forward.
Yeah, that was originally the model used to run on station data, and that was a big reason we moved away from it, was that we spent so much time cleaning station data, and then the question came up about, well, what happens if we want to model in a basin that doesn't have stations? So the HER data is really awesome for that very reason, that we don't have to have those stations there. The HER data does ingest some of that data. I don't know exactly to the full details how they do that. So I suspect that the HER data is more accurate in basins where they have stations that are monitoring everything.
Yeah, well, there's adjacent watersheds that with very nearby snow pillows. Well, some nearby snow pillows, but also snow courses in the case that I'm thinking of.
Right.
Yeah, we often, go ahead, Micah.
I said we have in the past extended the modeling domains of a basin to capture snow pillows and other stations that are outside of the domain as it would stand as we delineate it.
Great.
Right, and when we can, for instance, if we have a Tuolumne flight, we'll get as close to Tioga Pass as we can to do pit measurements, but we may not be able to be exactly in the basin. But using that proximity is quite valuable. Any other questions? All right. So next up is Kat Bormann, and Kat is going to talk about she's kind of going to wrap up all of these pieces that we've been talking about and that have seen questions. Looks like we've just had. Yes, Jeff, I agree. Will you please send Danny a text and tell him to get working on that paper? So at any rate, Kat, are you there? And you got your slides ready to go? See if I can find you. There we go. So this is work that we've it's two talks that are merged into one, and so we will. It looks like there's an echo. Oh, it's because Kat's speaker is picking me up. Anyway, I'll stop there and I'll let Kat explain.
Yes, sorry, we're in the same room, so it's a challenge. Okay. I'm a little puffed, I just ran up the stairs, but yes, this talk is two talks combined, and the main reason for that is I didn't really want to repeat a lot of what's been said. We've had a lot of awesome discussion this week, and so there's two pieces that I wanted to add to, and this is what we're doing. So the first piece will be the new snow water equivalent maps, snow water equivalent uncertainty maps. And so this is speaking directly to what the conversation was prior to me doing this talk. Jeff Dozier raised an awesome point, and this really is where we're focusing a lot of energy right now, and including with Grayson and a few of our other pieces of information that we're really trying to pull this piece of the story together, because the snow density part is right now the part we need to be focusing on. The second part of the talk will be about the river forecast centers and what kind of work we're doing in collaboration and in conjunction with those folks. And we're not talking just about the CBRC, we're talking about the CNRC as well. So it's going to be a big ride. Okay, so we've all heard that the snow measurements taken from the plane are really accurate. And so that's true. And so how do we know that? Gosh, we know that because we've gone out and measured it. And so one thing I do want to make a point of, and when we talk about evaluation of spatial data, and that's what we're talking about here, I think we need to move beyond the point, comparing a grid against a point. That doesn't make any sense to me. So I think what we really need to do is be looking at high density sampling. And that goes for not just snow depth, but potentially snow density as well. Although less so because the spatial variability is great. But what I'm talking about here is apples to apples. So if we have a 30 meter patch, 30 by 30 meter patch of snow, as you can see here, the LiDAR at about 2 points per square meter will get about 1,800 shots in that spot. So 1,800 individual measurements in that patch. And so comparing that to 1 or 2 doesn't make any sense to me. And so what I start doing now is, and I've been doing this for a few years now, is upping the points in that 30 by 30 patch. So right now, for this particular example that I'm showing you, I had over 200. So we're still comparing 200 to 1,800, but we're getting closer to the order of magnitude that we need to be comparing these at. And so when you do that in a whole bunch of exposed areas and then moving this into the forest, you can see that each big dot here or big triangle here is a 30 by 30 patch. And what we can see here is that in the exposed areas, we're doing really well. And our bias is about 1 centimeter at the 50 meter scale, which is what we've been saying. And this is why we've been saying it. It's because we've been measuring it. If you can see in the vegetation, you can see that we have a bias of 6 centimeters here, but this is kind of old. And so this is something I want to be revising very soon. We recently upgraded our snow depth algorithm in the forest. And what we're seeing when we draw transects through the forest, we're seeing us come down and getting retrievals into the tree wells and then back up out of the tree well. And so I think this bias that we're seeing here is to do with before we were kind of smoothing over the tree wells. Now we're getting right in there. And so I'm going to redo this plot next year. When you come to the workshop, you'll see hopefully everything will just sit on the 1-to-1. And so this is where we are with our snow depth. And one more piece of our snow depth that I touched on earlier was that we have a really good repeatability and an understanding of our repeatability at very fine scale on our bare surfaces. And like I said this morning, over the top of Half Dome and other monumental spots, our snow depth that we're measuring should be 0. Yeah. And sometimes it's not. In this case, it's a mean of 3 centimeters. And so we use that to adjust our snow depth to lock that in. And we also use this spread to inform this snow water equivalent uncertainty product that I'm about to show you. So we have a really good information to feed into our uncertainty calculations for depth. But like we said, it's not just depth. And so snow density is the hard piece here, much harder to quantify. So what we have is, right now we're using the modeled snow density where we get a spatial distribution that looks, something like this. And that's coming from the iSnowbell model. And, we can zoom into spots and we can compare. So here the model's saying 32% or 320 kilograms per meter cubed. We can compare against the sensor here. There's a lot of problems with that we all understand and are aware of, and there's uncertainty with that evaluation. We got to do it, but we need to have scrutiny with this evaluation. And so I think we need to have a lot more observations that we can trust to be able to evaluate the snow density model. But so what we do with the limited information that we do have, oh gosh, is we trace in time and we're comparing the model at all the sites with sensors all the time. And so what we do when we come in and we try and make that evaluation of how well is the snow density doing right now from the model, we grab like Wes said earlier, I grab every piece of information I can possibly get my hands on. So avalanche things, you know, any kind of observations that some random person's dug a snow pit over there, I'll take their data and have a look at it. But what you can see importantly is that here we have the model's in black, the sensor with a bit of spatial noise added is in blue. And you can see here for this particular flight at this location, the model is doing great, you know, and so we can say, okay, model's doing good given the information we have, let's proceed. The next flight, we come in and we can see, the model's kind of skyrocketed a little bit and the sensor's not really reflecting that. And so there's a temporal change in any kind of adjustment that we might need to apply in our operational setting. And then of course you get to here when we have a flight and most of the pillows are melted out. So that's a bit tricky. So quite often we'll get out there and take a few measurements ourselves. And the good thing is that snow density doesn't change as much spatially. So a couple of measurements will get you further than they will for snow depth. And so this is kind of how we go about it. And so quantifying the uncertainty to feed into our SWE uncertainty product. Hopefully with these adjustments, we're getting some of the bias out, and that's our main aim. And so we can see here again, this is kind of just an eye into what we do each flight and each survey. You can see elevation across on the x-axis and density on the y. And so the model that we got from ARS last year or earlier this year for one particular flight, I think it may have been May 7. It had its spatial distribution of snow density was quite high. It was all sitting up at about 550. And that's not what was reflected in the in situ measurements that we were getting from CDAC. Also the hole by hole information we were getting from the Hetchy crew where they went out and did their own measurements. And so you can see the dots and the circles are quite a bit lower than that. And so we looked at that and we said, okay, well, it seems like the model is overestimating. Let's nudge it down. And that's what we did with and you can see our distribution in the blue. So we don't actually go and match to these observations because there's uncertainty with these observations. We just nudge towards. And the idea is not to get a perfect match everywhere. The idea is to get rid of the bias. So we're not overestimating or underestimating across the watershed as a whole. So we're trying to push everything down to the one-to-one line, you know, not each individual point, but the collection of points. And so the deviation from that one-to-one line then becomes an estimate of our uncertainty, right? So if we've effectively gotten rid of the bias, which we've done to the best of our ability, then the spread around that one-to-one line then becomes some part of our uncertainty. And so this is what we use to then make our SWE uncertainty estimate. But I added this slide just as Dozier and Jeff Dozier, when everyone was talking about this. I think we really need to redo our model evaluation with a bunch more data. And we need to do that because the model has changed recently. The snow density algorithm has changed in 2017, 2018, got a complete new rewrite, and that'll be published soon. And so that's been evaluated as a part of the paper, but we need to do our own evaluations of that as well. The other thing is that the model, when we run it in, when ARS were running it in sort of forward mode during operations, they were making some changes along the way to tweak the model into the correct position. And that's what you would do in an operational setting. But in a science setting, it's really hard to compare changing model against observations. And so we really just need to have a controlled scientific experiment here to do that. And I can't wait to do that. So combining uncertainty from our snow depth and uncertainty from our snow density. So I've sort of spoken about how we might estimate some of those here. We can combine those using that horrible equation down the bottom there that I tried to hide. But basically, it's a propagation of uncertainty. And this is an example of what this might look like across the basin. And so what we're really going for is a per pixel on the 50 meters propagation of the snow depth uncertainty and the snow density uncertainty. And we can update our uncertainty estimates as we go along. And we do change them per flight. And so this is per flight specific information. And I want to point out here that the spatial patterns of this is kind of what you would expect, right? So you see a higher uncertainty in deep snow drifts, and that's where the impact of the snow density uncertainty is magnified. So it's kind of what we would expect, and this is what we're getting at. And so this product will be coming through. We've coded that up now. That'll be coming through in the next season for all of our products. Okay. Now just a little interlude. I love this movie. Okay, so now we're into the next part of my talk, which is the River Forecast Center work that we've been doing. And I want to credit some of this work to the Colorado Basin River Forecast Center for discussing what we want to talk about today and letting me show some of their work. Also, the CNRC has provided a whole bunch of data that I haven't even had a chance to chip through yet. So there's definitely a good collaboration going on here. So one point here is that ASO are actively interacting with both the CBRC and the CNRC River Forecast Centers. And so that covers quite a massive area of the Western US if you actually look at it. And so in Colorado, in the blue, we fly in these sort of green areas. And so we're getting a whole bunch of the snow affected areas in the upper Colorado. We want to get more. We have about 34 flights that are available. Not all of them are big enough areas for comparison with their model, with the CBRC's model, but we've got quite a good information to get a good start there. Flipping over to the Orange Basin, the CNRC's domain, we have yellow basins that we're flying, in the mostly Central Sierras. And so we have a bunch of flights there that we have not done we haven't done the full comparison yet, but we've just started. And so the idea here would be to first do the evaluation and see what the snow is doing in the CNRC and the CBRC's model, to see what the snow is actually doing in these models, and then how can ASO help, right? So just a quick overview. In the yellow box there, we can see that this is the way over a full watershed. This is the way that the Snow 17 model chunks up its basin. So it's kind of a semi-lumped model where it does elevation bands and it chunks up the full watershed into sort of modeling chunks. And so when we want to compare that to ASO, we really need to just chunk up ASO into those same zones. So we can do a direct comparison of aerial SWE. And when we do that, we can, get a nice little map of where the model might be a little too high or a little too low or doing pretty good. And so we can do this for every flight that we have data for. And I mean ASO data for, because the forecast centers have all of this. So this is a really good start to this work. And what we've done, what we've shown here is when we do that for every flight that we have, so this is for the CBRC. This is still a work in progress, but when we do that, we can see that the ASO zonal SWE across on the X, and the model in the River Forecast Center SWE, zonal SWE on the Y, we get a pretty good correlation. The mean absolute error is about 5 centimeters or 2 inches, and the percent error in SWE is about 19. So the mean error is like somewhere hovering around 19, oscillating inside. When we do the same evaluation at the CNRC's domain, this is very limited work, so I need to add to this, but you can see the correlation is still really high. You are seeing some basin differences. So we're seeing like the tuolumne is a little low when it gets high and things like that. So there's interesting information we can tease out here rather than, that we still haven't even chipped at. We can see the mean absolute error for in California is 19 centimeters or about 7.5 inches. But interestingly enough, the mean error in SWE is about the same as it was in Colorado. So we've got 22%. So we're sitting at about 20% error in mean aerial SWE so far. And so that's something really useful to know. But what that does tell us, if we look at them side by side, this tells us that the model is really trying to get at SWE, like the correct God's honest truth of SWE. Okay, and so if that's true, then inserting ASO data into this model shouldn't really affect the calibration of the model. We shouldn't really need to go through hoops to tweak and retune the model, because they're both trying to get at the same thing. And so this is sort of the theory that we're testing out now. And we're working with the CBRFC to start putting ASO into the RFC's model, on a research basis. And so this is some work that Pat did, and thanks, Pat, for letting me share this. I think this is a really great story and a good story to end on. So you can see a hydrograph here coming out of Taylor, I think it's Taylor, in the Upper Gunnison or next to it. And you can see the observed runoff is in red and the simulated runoff is in blue. Now this is the forecast without any ASO data. And this is a forecast made all the way back towards the 1st of April. And you can see that there are some differences, right? And that's what makes a forecast not perfect. But let's point out some of these. So the seasonal runoff volume is too high. So this area between this gap, this area between these curves shows that the forecast was saying there was going to be a little more water, 21% more water than there actually was. We can see some spikes here early on in the simulated runoff. And so that's probably that's the snow like sloughing off maybe some low elevation snow too quickly. So it's coming off too quickly. And so we have an ASO flight just before April 1 here. I think it was on the March 25. And so we can compare, going back to the comparison I was showing you before, we can compare the ASO snow, aerial snow, with the model, what the model was doing back here with its snow water equivalent. And can see that the model was overestimating snow by 0.4 to 2.8 inches, depending on where you look. Doesn't sound like much, but it's 25% of the SWE. And so the thing that I found pretty striking was that the overestimation of SWE of around 20% kind of matched the overestimation of the model with runoff volume. And I thought that was pretty compelling. I mean, this is just n equals 1, but it's pretty interesting. And so what happens when you do put the ASO snow? What if you grab that SWE and you put it in here into the model and you run it forward, making all the same decisions that you did here, but just with that ASO information? And you can see it tighten up. The hydrographs come together. And that's really what we want. So the seasonal runoff volume, the area between these two curves, has gone from 21% different to 4%. And that's just with one flight added here. And you can see there's a more constrained runoff timing. So we're not getting rid of this water too early. We're holding on until the right time and letting it off. And so this is really encouraging. And I do want to say that this is, one example. And it's in a research operational mode. Like the CBRFC are not in a position to ingest this data directly, but we're working towards that. And we're trying to figure out the best way to do that in the operational setting that we're all in. And I think that's about it. And there's my pretty picture at the end. Cool. Thanks.
All right, great. Okay, are you going to mute?
Yes.
For the time being, and then we'll go back and forth. So Kat, thanks for doing that. And I'll just add to that last result. My recollection is that when we have the second assimilation, I don't think we have the hydrographs yet, but when we have the second assimilation coming later in the season of the ASO data there, in those last results, we tighten up to a 1% uncertainty. So that now that was a season of very little precipitation after peak, and you can see that expressed in the observed flow. whereas 2019, I think, had a lot of late season snowfall. And so what's required then to keep those forecasts accurate is that quantification of how much precip we had and what that distribution of snowfall was and where exactly it's located. All right, so let's see. We have Jeff Doe. Well, let's see. So Ed Melcher is asking, how many locations within the LiDAR survey project do you use as a baseline to match snow off to snow on? Has any method been applied for correcting the potential GNSS errors within a large survey? Now let me hit mute, Kat, and you go.
Okay, so I'll answer the first piece, but then I'm going to let Jeff Deans answer the second piece. So how many locations? It varies between each survey. So we really want flat or flat-ish granite and not soil kind of contiguous areas. And so after we've had a big snowfall event or something like that, they're a little harder to find. So they do change, but we do have a set, so it's sort of a library in a sense of the places that we look at. And so we try and go for somewhere around 1,000 points of comparison for each survey, or yeah, for each survey. And Deems, can you talk about the GNSS stuff, please?
Yeah, for the GNSS errors, we use a real-time differential correction system for that, and then we check for line-to-line offsets and can correct those if they exist as well. But for the most part, those type of errors will also present themselves within the snow-free or snow-on to snow-off comparison that Kat's talking about. And we can then identify if those errors exist and go back and fix them. But for the most part, they don't. We've been pretty impressed with the ability of the systems we use to be both precise and accurate across the full domain, across a long flight.
And Gus asked a question and then it just disappeared, but he was asking if the CBRFC work is based on direct insertion. It is based on a direct insertion. We're talking about, I mean, I think Pat can speak to this about more explicit assimilation techniques, but with the accuracy of those, I think there's the direct insertion is good. Pat, are you there? You are allowed to talk.
Hey, what's the question?
So Gus was asking if the work with the CBRFC was direct insertion, to which I answered yes, but that we had been talking about more refined assimilation methods.
Yeah, it's just a wee change in the model. And in this 1 year in this one basin, it worked out really well. This is one of our really well-behaved basins that's well calibrated and we think represents reality pretty well. So yeah, it's just we took what the model had and changed it, the SWE directly.
Right. All right. Thank you. Let's see. There we go. And questions. Okay. There's a side conversation going on over there. All right. Great. Did I see? Oh, those are getting moved off. Okay. All right. Kat, thank you. And thanks for closing that out. So really quickly, I just want to show a couple of slides just to, there were questions this morning and we've heard the questions before. about that forecast number that we're talking about, largely when we're talking to the media, not when we're talking to more detailed to our colleagues here. So let me pull this up just to describe what was referred to this morning, and likewise in some of the other media in terms of that accuracy. So I want to reinforce that we're not under the impression that ASO on April 1 knows the snowpack and knows all subsequent precipitation in order to get the accurate forecasts. Precipitation is a critical part not only of what we're measuring, but also the ability to forecast out into the future. This is the so-called grammar plot from Olivia's talk earlier for the Tuolumne. This is the modeled full natural flow for the Tuolumne above Hetch Hetchy and Cherry and Eleanor across several years of data. And this is using the precipitation measurements in this empirical relationship from the Tuolumne precipitation gauge. In the past, they have, Chris has used the precipitation at Hetch Hetchy, or I should say at the O'Shaughnessy Dam. They recently updated it to use the Tuolumne precip, and that seems to work out much better. The value that we're quoting, and so in terms of an ASO forecast, and this is an empirical seasonal flow, is the minimum possible seasonal inflow. And so I'll refer back to Kat's talk and the slides from Pat's work. That was 2018, and with the assimilation of the ASO data early on, in that case, there was very little precipitation that came afterwards. And so that is not inconsistent with what we find in the Sierra Nevada as well, that solid information of that peak SWE distribution gives you the best possible, at present, the best possible understanding of your snowpack and the ability to forecast into the future, given likely precipitation scenarios as well as climatology. And this is a slide that is borrowed out of Chris Graham's talk from a couple of years ago. And as he says, it's critical for forecasting operations. And likewise, what Jenny Fromm presented in her talk as well, with those early understandings of what's that minimum flow that's going to be coming. So that, Gus and Pat, that's what we're referring to with those forecasts. This is just an example as well from, I think this was 2017, and the spaghetti ensemble here, that's the modeled inflow distribution in the Tuolumne from the CNRFC. The minimum CNRFC flow is right here. And I think we're looking at what, 240,000 acre foot difference from that May minimum inflow forecast from the empirical relationship with ASO. And then finally, this is just a look at the numbers from CNRFC and DWR for this year, and then those ASO numbers with precipitation scenarios, and that's the full range of precipitation scenarios, not likely scenarios, but full range. And then Tuolumne's model, the HFAM, likewise constrained by ASO, and those final numbers came in here at 686, so very close to where these were targeting. So at any rate, yeah, just to avoid some of that confusion about what's out there, and it's tough talking to the media I had my first experience with that was back in 2014 when we first realized dust and snow impact and how many weeks difference there was in meltout due to excursion in dust and changes in albedo. And it was at the American Association of Geographers meeting in Denver. And I gave a talk, and I had a whole bunch of friends, including many of you in the front row. And I made a joke at the end about how we have the cows to thank for this. And what I didn't realize was that on either side of the aisle, dead center up front, were the main environmental reporters for the Denver Post and the Rocky Mountain News. And they then had that as a headline for the story. Cows to blame for early snowmelt runoff. So I got to learn something from that. Any rate, let me see. Another question has popped up. Do you change the aerial extent at the same time? Gus, I'm not sure what you're saying, so let me defer to you there. Okay, you can talk.
Thanks, Tom. I actually had to step away for just a second, but I did hear most of your piece, and I appreciate you showing that stuff. I think I understand the difficulty conveying some of these, more complex pieces, but my biggest concern is just not letting that overshadow, the key modeling work that's still ahead of us to truly realize the value of the ASO. Yep. Monitoring. That's really my main point, and I appreciate you taking the time to address that. I don't know if you had another question at the end that I missed or not.
Well, it looks like you says, do you change the aerial extent at the same time?
Oh yeah, that was just following on the direct insertion. Is there also like an aerial extent change that happens related to the spatial aerial extent information?
Kat, are you, you look like you're leaning in for the mute button. I'll hit mute.
So Pat Quamos can probably speak to that better than me, but I believe it's lumped, right, Pat?
Yeah, it's lumped. There's an aerial depletion curve. I'll have to look and see. Yeah, it would automatically adjust the aerial extent when you change the SWE if it's below a certain threshold in the lumped model.
Yeah, I understand that. Thank you.
Yeah, I'm trying to juggle it. So, all right, great. So this draws us to a close, and I'm not gonna keep us here long. We're a half hour over, which is pretty remarkable. We're only that far over. I want to thank all of our presenters and all of the attendees and the panelists. This is dealing with the meeting digitally is in some ways not as easy as it is dealing in person, and there are a lot of benefits. On the other hand, there are a lot of benefits to being in person. On the other hand, I think we get more people with us. We had 168 registrants, and I think reached everybody across that list across the week. And so I just want to express our appreciation to all of you for making the time and making sure you were here. And I personally want to thank the ASO team, in particular Liz, who has orchestrated this and kept us on track and made the organization of this work out really, really well. Let's see, I have heard from Ryan on his size, and I'll get in touch with Ethan for his shirt. I think in summary, we're looking at, we still have some of those next questions about the modeling going forward. How well can we do with the precipitation forecasts, and how far out can we reach those? And then likewise, these activities with the river forecast centers those are really important for the implementation of the program in the Western U.S. And I'll also say that the relationship with Dave Gotchis, with Wharf Hydro, and likewise with M3 Works, with the work that they're doing not only on modeling the snowpack, but starting in as well with the flows, is really important. And to the community, I think you can tell we're really open to interacting with you, and we want to. So thoughts that you have, desires to access data, and likewise, once the data distribution and analysis tools are out there, it's going to be great to have your input on that. And I'm thinking that sometime in the next couple of months, we may open up a 1-hour meeting per week, or maybe every other week, to have essentially a workshop with anybody that wants to come in and meet with us on ideas that you have, results that you want to present, and that way we can keep this community going together, and not just being together once a year, and hopefully next year here in Mammoth in person. Let me ask the team, do you guys have anything more that you want to talk about? Jeff?
I'll just echo your thoughts, that I want to thank all of the participants and speakers that we've had. We're going through a transition from out of NASA to a company that's had its own challenges, and part of those challenges is kind of maintaining our relationships with our collaborators and our research colleagues. And that comes, there's a little trepidation there on my part. I want to make sure that we maintain all of those things while executing a successful transition. And this week has really indicated to me that we're doing a good job with that, and I'm really pleased to see all the participation and all the familiar and new faces involved in this workshop. So thanks to everyone for your participation and making this a lot more than just the ASO team shouting out into the internet. So thank you all. It's been a great 4 days here.
All right. Well, if there's nothing more, and I don't see any red lights in chat or Q&A, we will draw this ASO workshop to a close, and look forward to seeing all of you soon, and likewise seeing all of you hopefully in person here in Mammoth Lakes next year. Pray for snow. Bye, everybody.